So, morning everyone. So the guest lecture here is on shallow to deep non-IID learning. So IID here refer to the first I refer to independent, and then ID refer to identically distributed. So together, see IID. Non-IID means so either the data or attributes that do not follow this IID assumption. Okay, so this involves a lot of work from some of my ex-students, but actually can't cover everything because only 4 hours lecture here. So where do we go? We just do maybe one break at around 12 o'clock and for about 20 minutes. And then we just continue. So for reference and materials and lecture notes, you can actually find, from this website here, non-IID.datascience.org, and you can find some from the YouTube maybe on the old version. So today's agenda, I mainly focus on some of the key concepts related to IID learning in the classical domain, and then explain the concept of non-IIDnesses, and focus on just briefly introduce some of the recent technique developed for non-IID similarity learning, matrix learning, representation learning, learning interactions and relation, what I broadly call coupling, and learn heterogeneities. And I also illustrate a few specific areas related to pattern mining, statistical learning, recommender system, behavior analytics, visual learning, outlier detection. And then I invited Jilin to share his talk, his work and relevant work on the out of distribution detection in a deep neural network. But of course, there are many other things that could be related. For example, non-IID for document analysis, for ensemble learning. Particularly nowadays, I think a lot of interest in federated learning or transfer learning. I won't be able to cover them today. And there's another recent topic on domain adaptation, and that's also somehow relevant. And during the discussion time, I'm more than happy to discuss particularly like federated learning and transfer learning, domain adaptation, if there are some questions there. So first of all, I think it's really important to understand the concept IID, and in the classical domain of analytical learning, cover almost everything from mathematics, statistics to the general AI or whatever you call data mining, machine learning, computer vision, pattern recognition, image processing, signal processing, etc., etc. There's a very fundamental and basic things, the IID assumption. And I want to summarize and I want to explain to you and what it is and how they were incorporated into this classic analytical learning and what a problem they cause. So first of all, formally, from mathematics and a statistical perspective, how do we define IID? And typically in statistical reference, you see something like IID, right? And nowadays, I think more come to this capital IID. So what is given like this? Given a data set consists of X and Y, and it's got an N tuple of input and response. And in this tuple, xi and for each xi and yi, and we assume the xi and yi is independently drawing from the distribution pxy, right? So that's the way so we have this assumption, right? So what does this mean, right? So we see xi and yi drawn from IID drawn from a distribution pxy, and there are a lot of assumptions behind. It means so xi and yi are independent or is independent of xj, yj. Means those samples are independent. And second thing is that all sample in this data set, they follow the same distribution, right? So that's why we see it's IID, right? And then the learning task is to learn algorithm py given x, use things like Bayesian rule, whatever, so you can actually derive and get this, posterior, right? So that's a typical mathematical statistical setting for IID. And further, I can abstract this assumption to, to this. So given a problem, a learning problem or analytical problem, so we have multiple data objects or data sources or modalities or domains, right? Or whatever setting. So represented by O1 to O3, so refer to different, source or entity or whatever have. And typically we have a learning boundary here, right? Learning boundary. And then in the reality, we know, so there's some sort of like a relation between the, objects, data source, modalities, or domains, right? So there's some like indirect or direct relation, strong or weak relation, for example, economic relation, political relation, or other type of relation, right? And the relations could be different, right? Could be different. So that's the reality. And also the entity here, O1 to O3, they are different. So typically we see they are heterogeneous. Heterogeneous mean many things. I explain that later. So in the classical IID setting, so what do we have? We assume these objects, they follow the same distribution. So we basically assume they are homogeneous, right? They're homogeneous. And then second is that, so they are IID drawing from the same distribution. So basically we assume, so they follow the same distribution and they are independent. Independent means so they, so you draw one sample of one, it won't affect O2, right? So they are independent. And then the whole learning problem is to learn based on these IIDnesses in the original problem, and we then learn objective function. For example, if we want to determine sample O3, and we learn objective function D3, right? So this will be D3, and based on a particular baseline, like could be a center, could be some other things like the ground truth, etc., right? So we learn this objective function, and then determine which cluster or which class or which pattern O3 belong to, or whether O3 is an outlier or not, right? So those basically cover the typical analytical learning problems: pattern mining, unsupervised learning, supervised learning, outlier detection, etc., right? So that's a very common setting. And with this setting, so you can see actually many algorithms or models have been generated in the literature. So in machine learning, typically we categorize them into, machine learning analytical method into two big families. One is discriminative learning, another is generative learning. So let's explain a little bit about what is discriminative learning and where IID may exist. Right? So in descriptive learning, so our purpose is to learn a model Py given X. And we want to separate, and we want to determine, the label of X as an example, right? Or we want to separate, the Yj, right? So we want to have a discriminator to separate those samples and give them, a clear label, a clear partition or something like that, right? So that's discriminative learning. So this applies to both supervised and unsupervised learning, and also deep learning, for example, autoencoder, right? So we want to have an encoder and decoder. So, and you calculate the construction loss, and based on construction loss, you have a ground truth there somehow, right? You want your autoencoder to be discriminative and to separate, and have a clear, clear margin. But in the variational autoencoder, it could be a different story. And some other important ideas in deep learning, like adversarial or contrastive learning, that also could be based on this discriminative learning principle. So when we do this, the basic assumption is that, so our task is to learn the model on each individual sample xi in the set, in the whole data set. To learn this, probability function, or could be other, just a learner, right? And to determine, to separate yi from yj, right? And for each target yi, and we assume the target yi is conditionally independent, giving it the independence of xi, right? So that's the assumption we typically have. And typically, we may not have a very specific distribution assumption on each sample xi, but in a particular learning, we typically just assume all xi follow one specific assumption, one specific distribution, right? So it means, so all the data sample xi are ID, right? So here you see there's independent and ID, so there's RID, right? That's in a typical setting, right? But in the more complex setting, as I will introduce today, you will see actually could go to the non-IID for discriminative learning. So another big family in machine learning is called generative learning. And the idea, the principle is, so we learn a joint probability for Pxy. And when we do that, so we have basically two tasks. First, to learn conditional probability of the sample x given y, and assume we already know the marginal distribution of py, and then based on the Bayesian rule, and we can derive to get the posterior py given x, right? Okay. And this idea, actually general idea, applies to unsupervised learning, traditional pattern mining, like negative sequence analysis, for example, and a lot of mathematical estimation approach like LDA or Bayesian network, right? So if you work on the probabilistic graphical model, so you will see, you have very common approach. So I will introduce a statistical learning where you can see this generative learning process. So what are the assumptions behind this generative learning idea in the classical domain, right? So what we have is that we assume y and yj are ID, and xi and xj are ID. And we assume, so for the I samples, it actually has the ID sampling process. Sampling means we draw each sample from the distribution in ID fashion, right? And because of that, and because we assume the xi and yi, they can be ID drawn from particular distribution, so then we can actually calculate or estimate or approximate the probability of x given y using, based on the sample. So that's basically evidence-based, right, in the statistical term, right, based on the, and then further we use a Bayesian rule, and we can derive to get it, to get the posterior, right? And when we do that, as we will explain in the statistical learning, so you will see actually, here we typically have this ID, local conditional independence setting. Without that, so the Bayesian network and the Bayesian learning could be in big trouble. And that's also why Bayesian learning actually, or probabilistic graphical model, used to have some bigger hurdle there and couldn't really move forward. And nowadays, and more to combine, the Bayesian or or statistical process with deep neural model, and then, combine the two learning paradigms and to resolve some of the constraints in the traditional Bayesian learning, particularly in the SVI, statistical variation. I will explain that later. So the distance measure, so you can review, if you like, you can review the different distance measures or distance functions or similarity function or dissimilarity function. And when you use them, very importantly, I think you need to really look at them to understand the basic settings and assumptions, whether the assumed objects or variables are IID, or put it in another way, variables are random. Usually we see in that way, right? So like in the very basic one, like Euclidean distance, Hamming distance, or Mahalanobis distance. And when you do that, so you need to think about whether they have the ID assumption. And then in opposite way, you need to ask, what if the objects and the variables, they are dependent, or if they follow different distribution? For example, if you simply use Euclidean distance and x1 and x2, they are dependent and they follow different distribution. Can you use it? Right. And then same thing, for Hamming distance, and I will explain using examples to explain that, so the traditional ID assumption could cause some major issue. And further, in the many statistical measures, when we do the statistical, for example, like variance, we calculate the variance based on mean, we calculate the covariance, for two sample, xi and yi, or we do the cross entropy or KL relative entropy, KL divergence. When we calculate all this kind of thing, either just for one sample or two sample or two model, two distribution, all these, they have some particular setting there. And we have to really understand, the setting. And in the traditional settings, typically they follow the IID. They follow the IID, and you can actually need to really to understand the settings. And for example, so if xi and yi, they are dependent. If they follow different distribution, can you still calculate covariance between x and y in this way? And similarly, for the entropy, right? So you have two models, P and Q, but they are heterogeneous, but they somehow also, like in ensemble learning, they're somehow relevant as well. And how can we calculate, the cross entropy or KL divergence, between the two model PQ, right? So I think these, there are seems many, questions we should really think about, when we use those existing, settings or given theory or functions, right? So, they could actually lead to some trouble, when you actually simply take that. So let's give you a little bit more information. For example, there's a K-means model. So I think everyone knows K-means here, right? So you get a K-means, so have the objects, and given each sample, we want to calculate, the distance between the sample and a given mean, right? Basically a center, right, of each cluster. So this cluster, the green, we have one particular, we choose one point as the initial center, and then we calculate, and then we keep updating, the center and build the mean, right? And then we try to minimize the distance between, the samples within one cluster, and then maximize the distance between two clusters, right? So that's basically K-means idea. Similarly, you can incorporate, fuzzy membership and build a fuzzy C-means analysis. There are many, like, K-means, etc., etc. right? So what are fundamental here? So the thinking really is most important, right? So what are the fundamental thinking behind? And when k-means was created, or when we use k-means, we have to understand that. So here, basically, we assume the different, so we have two target here. One is a sample, another is a center, or the baseline, right, or the benchmark to be compared, right? We have two things here. So here, if xj and xj1 and xj2 are dependent, so you're going to see, for example, there's a green point here and a yellow point, they are dependent, all right? How can we still use this objective function, right? And we usually first understand, this cluster, they may follow distribution, and this one may follow another distribution, right? So if they follow different distribution, and likely, so the way to build the center, probably should really consider their characteristics, right? And when we consider that, we see the classes are dependent, or classes are dependent, or classes follow different distribution. Can we still use these k-means, the basic k-means, right? So that's what I explained. So when we have this basic k-means objective function like this, we basically assume, there's object IIDnesses and a cluster IIDnesses. And we understand there's a global, right? The global issue, there's a global learning issue, and then we convert it to a local learning task for each cluster. That's why you have this, K cluster to be optimized, right? And all these actually have some very strong assumption behind. And particularly another thing I want to mention to you is that as a global partition, there's a global learning task, but we converted the global learning problem to a local learning problem. And so if the clusters, they have some global constraints or whatever, or non-ID, whatever. So how can we simply convert the global task to this local learning, solution, right? So I give you this is for you to think, because I think you guys are doing PhD, and I think you really need to focus on the thinking and understand, so when we can use what and why, right? And so it's not just about what and how to use it, it's more about why and when we cannot use it or when we can use it. And similarly, decision tree is a very typical approach, it's a very classical approach. So what we have to do is that we build information game, right, as an objective function, and that is built on the mutual information of the data set and their, each attribute, right? And also, and this can be converted, to the entropy of the set and the entropy of the set condition on each attribute. And then you can split, the attributes, right? And based on the attributes, the game, and then you can split, from initially find, root attributes, and then to the lift, and then each lift correspond to a cluster class label, right? So that's basically a decision tree. But if you look at this function here, it eventually converted to the probability of class and probability based on the specific, sample, each sample I, right, for attribute A, right? So here, so if we know the attributes, they follow different distribution. Second, if the attribute, they are dependent, can we still simply use this information game function as an objective function for decision tree and to build the tree model? And the trees are very common, right? So we know there's a main tree model is a tree family, random forest, and ensemble trees, etc., right? Use a tree model, XGBoost, right? So here there are really some strong assumption behind. So as I mentioned, if object the two objects, SK and SC, they are dependent. If the attributes A1 and A2, they are dependent. If the classes, they follow different distribution, can we still use this, information game, function to split, the attributes and form into rule-based, classify. So, and further, if you look at the KN, right, it's another classifier. And in the KN, so basically for the target, and we choose a K nearest neighbor, and then use the majority sample, their label of the majority to determine this target, right? So that's basic KN. But in this case, so I'm asking you to think about, if this red, we know this red triangle, A1, A3, and A4, A5, because they are all red in the triangle, but somehow, they may be relevant, right? And may be coupled in some way, right? And they may follow similar distribution in some way. But for some other critical reason, these three, they do not really sit in the, in the neighborhood of this target. And similarly, for this blue square, and if they are dependent, this one depend on this one somehow, or is this even weakly dependent in some of the attributes, and then there's still maybe some sort of relation. Then so the basic can could generate really misleading outcome, right? So another thing in the traditional machine learning, and a very fundamental thing is called cross-validation, and we usually have to use that. In the deep learning, probably don't worry too much, but you still have the batching, right? And in the cross-validation, so the key folder, right? So we have the data, we split the data to multiple, sets, folders, right? 10 folder, for example, and then for each training, and then we can choose, split the data in the training and the test, and then in the training we choose some of them, to train the model and the test on the remaining one, right? So in each round, and you do multiple round, and then you do the average or whatever, and then produce the outcome, and you do the test on the rest, right? So that's basically cross-validation. When we do cross-validation like this, so we particularly emphasize we need to do a good stratified sampling, which is very, very important. So if the sampling is not done properly, it means the cross-validation does not really generate a good outcome or reliable sound outcome. Right? But how about if you have really high dimensional data, and you want to do a really good sampling, but the data really, the samples are coupled in some way, in a way. So randomize them, it becomes really a difficult task. It means, so in the randomized, so we want to make the data samples as IID, that's basically, right? We assume there is one distribution, and we can sample, the folders from this data set in an IID way. So that's basically a very fundamental assumption in the K-folder cross-validation. But if the data, in the data, samples are non-IID, so that you cannot really have a fair way to do IID sampling. That's basically what I want to say. And then K-folder cross-validation would not work, right? So a typical example is in the, nowadays people call out of distribution detection, right? So you have, we'll discuss that later. So in the sampling, training data and test data, so they follow, there are some samples that follow different distribution, right? If they follow different distribution, then encode in the out of sample set, the distribution different from the in sample set, right? So that's called the OD problem, right? So, but that's for the learning process. So you split into training and a test from the learning process perspective, right? So in this, but even when you do the key folder training, actually you still have this issue there, right? So here, of course, we only talk about the complex data. If the data is simple, we don't worry too much, to be honest, right? And then what could be the outcome if we simply apply the ID analytical learning assumptions? So the outcome could be even use very simple data. So I mentioned this later again, in a very simple UCI data. And you will find actually some of data set use a different method, the different curves represent to different method. So use a different method, you will find actually some of the method, most of the method, they probably basically produce misleading or incorrect outcome. But we still compare, try to create a new algorithm and compare with the existing one, use them as a benchmark. But unfortunately, the benchmarks are wrong. They do not really produce, a good outcome, right? And sometimes, the problem much simpler, or the data is much simpler, and most method you could produce just, simply, the correct outcome, right? So that's why nowadays, and more people realize the bias issue or fairness of bias become a really critical concern in statistics and in deep neural model, right? Okay, so you can discuss about that further. I think if some of you work on the bias or fairness, there are specific different type of bias or fairness issues in the learning, and that actually goes beyond the fitting issue. So we understand in the overfitting or underfitting, in the fitting, if we don't do it properly, it could include bias or variance, right? But it goes beyond, the fitting, and actually, this bias could have come from, just a better model, right, or better learning process. But today I want to talk about that. It is, so what I want to say is that the bias could be caused by, ID assumption in many cases, right? So now I move to the important concept called non-IIDness. And previously talk about the IIDness. Now we talk about the non-IIDness, right? So mathematically, so we mentioned this earlier. Let's say, we assume, so we can draw a sample from a distribution, ID drawn from a distribution. So that's mathematical statistical, ID assumption or ID way to do it, right? But as I mentioned earlier, so what if the samples, they are coupled? If they are coupled, we cannot really independently draw, right? We cannot really make them independent, right? And then it means the independent I, the first IID, the first I will not hold, right? And secondly, so if we want to draw the two sample from the distribution, but what if they follow different distribution? Which means, so in the data there are multiple distributions. If there are multiple distributions, and typically in the multi-model, cross-domain, multi-view, etc., that's very common, right, in reality, right? So it means they are heterogeneous. Then it means the ID, identical distribution, does not hold here at all, right? So which means this ID definitely would not really hold in the, in the reality, right? Okay, so as I mentioned, so if you have a high dimensional data, for example, d-dimensional, right? So each variable here, each sample is a d-dimensional vector, right? And if the two features, right, xm, sn, they are independent, and then can we still use, those statistics I introduced early on, right? Or if they follow different distribution, it means the prior of M or N family, it could be referred to two sets, right? and they could be different, right? And then we probably cannot use k-means or decision tree in that way, right? And if it is a supervised learning, you've got classes yi and yj. If yi and yj somehow affect each other, so later I will give you an example like in outlier detection in supervised way. So you will see actually, if the classes they are somehow dependent on each other, the results or health results actually depend on each other. And another question is that if the labels follow different distribution, right? How to build an objective function, right? So I think simply there are many things we have to really think about it. And in a high-level way, we can summarize all those questions I just asked into two major concepts. One is heterogeneity. Another is what I call a coupling and interaction. So heterogeneity refers to the different data type, different attributes, typically like mixed data, or different data source, different modality as I mentioned. And for each attribute, it may follow different distribution or different format or structure. And the relation could be different as well, right? And even we can extend this to like ensemble learning. You've got multiple models, and we understand each model follow different principle and idea thinking, right? It means the models are heterogeneous, and the results could be somehow heterogeneous as well, right? So in the traditional term, we simply say they are non-identically distributed. But here, heterogeneity definitely goes beyond non-identically distributed. So here we still use a statistical traditional way for easy communication, but actually heterogeneity goes beyond distribution. When we see identically distribution or non-identically distributed, we mainly focus on distribution because that's a common way to measure the process, right? But in reality, as I mentioned here, if you have different structure or different relation, of course the distribution will be different, but there are other heterogeneity here. So that's really important to understand this. So another thing I broadly call it a coupling or interaction. So the term actually comes from cybernetic and mathematics, statistics, et cetera. So in statistics, mathematics, we have the interaction, right? And feature interaction, variable interaction concept, right? And in the cybernetic, you see you have system variables, they could be coupled or loosely coupled or strongly coupled, et cetera. And these coupling interactions could happen between the two values or multiple values or two attributes or two objects or multiple objects. So there are different level, different, target, and then there are, they could be coupled strongly or weakly, right? And if you have different distributions, and we understand in a Gaussian mixture, so the mixture distribution could be somehow coupled as well, right? And then form and unify into an interesting complex, distribution, right? A compound distribution, right? And a relation typically may not be so easy to separate. You see, that's why we often have geopolitical. It means geo and political, they couple. Right? You can't really separate this to political relation or other type of relation, right? So this means simply you follow the traditional term for a non-independent and then together non-IIDnesses, right? Okay, so I'll give you some further example about the couplings. For example, that could happen between the numerical, categorical, or textual, or mixed structure of data, syntactic, semantic, or from other perspectives like economic, political, organizational, or social aspects, right? And today, actually, in the machine learning, we actually already go beyond the more objective, neural, categorical, textual, the data type to other relation, like a social relation. That's typically, in the recommender system, we work on the social relationship, right? And in many other cases, and in the enterprise data data analytics, we actually consider the organizational factors or cultural factors, economic factors, et cetera, et cetera. In the latent space, we have to consider the uncertainty or random or unknown variables and the relation there, right? And in the deep learning case, we simply see there's a latent relation there between the latent variables, latent factors, features, right? So when we use this term coupling interaction, so as I mentioned here, you probably now get a sense that go beyond the existing mathematical relation like dependence, correlation, association, causality, and they can be quantified in quite a clear and exact, mathematical term. But in many cases, and when we involve geopolitical, organizational, cultural relation, it could become quite difficult to quantify by some of this, right? But of course, when we quantify the cultural relation or economic relation, we may build on top of this, mathematical relation and add more things into it and then to enhance it, right? Okay, so that's why I see that mathematically there's well-defined relation either pairwise or for multiple and more specific and descriptive and more explicit in some way as well. Explicit means you basically build them on top of the observation. But as I mentioned, if I summarize here, so in a real world problem or data, so it may involve explicit and implicit relation or interactions, or quantitative or quantitative, or specific or comprehensive. It means you've got a hierarchy as well, like from local to global, et cetera, et cetera. But of course, it's referred to always complex system, complex behavior, and complex data. For example, so we try to quantify or compute the behavior. So see, in stock market, so it's buy or sell or different kind of investment behavior or trading behavior in the market. And each behavior can be represented or related to a particular actor. And then there's some operation can be attributed to different kind of property, for example, the time, price, volume, et cetera, right? And same for other behavior. We understand in a stock, if we want to trade or for a trader, the multiple trading behavior is somehow, related in a way, right? So how do they relate to each other? I mean, for the same investor, there could be temporal relation or spatial or other type of relation, right? And across, the transactions in the trading engine, so we could find actually, there are sort of like, investor behavior relation that's called an inter-coupling between them, right? So later I will give you example about pool manipulation in stock market, how to model the group behavior by considering their, behavior relation for one trader and behavior relation across traders. Right. And further, if you are interested in that, you can further explore the behavior coupling could be measured or could be quantified in many different ways, perspective, and further decompose that into different aspects. So if you are interested in that, right? So that's why nowadays, behavioral AI become more and more recognized as an important area. And some of you probably know, there's a behavioral finance or behavior economics. It's more from the psychological and from, some other quantitative like a regression perspective. But we can actually understand or quantify and compute behavior in a much more comprehensive way, right? Okay. So by now I can summarize the non-IID and non-IID learning, the concept in this way, in a very high level, in a universal way like this. So given the same learning problem I introduced early with heterogeneity, with coupling interactions, right, between the objects, modality, domain, view, or data source, et cetera, et cetera. Federated learning or whatever, multimodal, multitask learning problem. And we assume we have to respect the non-IIDness there, non-IIDness here. And then the learning problem is that how can we model the heterogeneity of the target heterogeneity, right? So we want to respect the heterogeneity here. And then how can we learn the relation between, the samples, right? And then when we build the objective function for all three, we want to do clustering, classification, outlier detection, pattern mining, for example, and we have to learn the objective function. And when we define the objective function D3, and then we have to consider O3 actually is different from O1, O2. It different means it may follow different distribution. It may have a different structure, or it may be engaged, with O1 in a relation that is different from the relation between O3 and O2. And more for us to consider is that we understand O1, O2, they all related as well, right? In some way or in multiple ways, right? And how can we actually consider the D3 relation or build the objective function for D3 by considering the relation between O1 and O2. And also another part is that, so we understand we already get the D1 and D2. Would D1 and D2 also affect D3? Right? So in a complex non-IID setting, like in non-IID federated learning, we probably really have to consider this. But unfortunately, in the current federated learning, that has not been really the case, and typically just focus on heterogeneity and the really complex coupling between the local source and the global model, and the local models have not really been considered at all. Right. So then we have to build a function which say O3 will be affected by R13, R23 in a high level way, I put it this way. And then the benchmark O here is affected by D1 and D2. It basically means we have to consider inference of O1 or 2 on this benchmark, and also the interactions between O3 and O1, O3 and O2, and also O1 and O2 into this objective function calculation or building. If we think all these actually in different machine learning or AI domain or whatever you like, the areas related to representation learning, related to data preparation, like denoising, transformation, cleaning, discretization, missing value estimation, etc., etc. Or if you do the similarity, d-similarity learning, the matrix learning, etc. Or if you are interested in statistical learning, you use graphical models, you use hidden relation learning or Markov models, etc., etc. And in another case, if you want to do the risk analytics outlier detection, right, from the value to feature, etc., etc. And if you work on the NLP, and if the word and the sentence and documents, they couple interact with each other, in different ways, semantically, or in other ways, and also in other cases, you work on the database retrieval, information retrieval. When you do the search, you design your search algorithm, and between the query and the answer, and within the queries, within the answers, and how to consider their relation, right? And this thinking apply to many other issues. If you work on feature engineering in particular, in the shallow case, right? So would the features be coupled with each other and they follow different distribution, or they are heterogeneous? And in the recommender system, and same for behavior or for vision, image processing, etc., etc. So this is actually, the non-ID thinking, the non-IDs may be held in all these, areas or sub areas, or algorithms in the machine learning or the broader analytical learning family, right? And that's why I see this non-IID, if you think way beyond IID, and that actually goes to each specific area. If we work on in a specific area, you could actually, or you may need to rethink, whether there are non-IIDnesses in the data or in the system or in the behavior or even simply in the attributes, right? Okay, so this applies to nowadays like OD or federated learning as well, and many other traditional topics as well. So I will explain some examples about some of them. And in separate group, actually, they work on something called beyond IID information theory. If you are interested, you can find some of the workshops they organize, and they talk about, more broadly, how to incorporate other theories into the information theory or enhance the current, IID-based information theory. So that's the first part. I actually try to slow down and focus on the concept and make it clear. And so now from here, so I started to introduce some of the technique. I just illustrate some technique for each topic, because as I mentioned, you could see it's just so broad. This problem is fundamental and is overwhelming. It means, it could apply to any learning task or learning problem or analytical applications, right? So by the way, if you have any questions, you can use whatever way you feel comfortable. Either send me the question in chat, or you can unmute yourself and to ask the question. So now the first technique, first area I introduce related to non-IID similarity learning or matrix learning. And there are a lot of work done in my group related to incorporating the different couplings, hierarchical couplings, into the similarity learning or matrix learning. If you are interested, you can find some of the papers. I just list a few here. So I just illustrate one technique, and a very basic one, which nicely, I guess, to explain the idea of hierarchical different coupling when we do the similarity learning, and called similarity-based representation, right? So the rationale is that, so for this picture, if we do a picture learning or imaging analysis, we find two persons sit on this chair together at this particular moment. So we want to understand why these two persons, they sit together here at this particular time, at this place, in a mathematical, quantitative way. So that's basically what we want to do, right? We want to find the reasons why. Right? So, computing way, right? And how to do that? So if the data can be converted to a table, a tablet, typically I think, like in image computer vision or in the business analytics, we can, in many cases or most of the cases, we can actually convert the data into a tablet structure, right? So with the attributes, multiple attributes, to describe each object or entity or data sample, right? Then you got a value corresponding to each customer on each attribute, right? And then if you work on multiple model to cluster, for example, we do the cross credit fraud detection, right? And we could have different detectors, and this you can have multiple models or rules, right, implemented in production, and each rule will give you an alert whether it's a fraud or not. Right? If it's a classification problem and then it is not a binary, you could have multiple class, right? And if it is a clustering model, and then it could give you the cluster, right, and label each object into one cluster, right? So overall, we can generalize, the general learning problem into extended information table like this with object and with labels and with attributes, and then you could have some label here, right? Some of them could be label, and then you could have some models here, and the model could give you the label, actual label for each, right? And so with this, the overall idea we want to have here is that, so within each attribute, basically means between the values of each attribute, what are the relations between the values and how can we model them? This we call the intro attributes, coupling learning or interaction learning. So in the statistical mathematics, you have a feature interaction, right? So model that. But now we talk about this in ways to model the value interaction. And then for the the values in attribute A2, would they be affected by another attributes, A3, A4, or other, right? It means there are interaction between, between the values from different feature, basically, right? V11, V12. So that's what we call it, feature interaction, right? In the mathematical statistical term, right? And if you have models and label, and we understand that the models may be independent in where you see I just created this model applied on the data, but the actual, the labels generated by each model for this problem, it could be actually relevant, even though you label it by different. If this is a binary issue, you would, M1 would produce yes or no, and same for MQ, right? So it means yes, hell, they are related, right? Right. So should we model their relation? And then further, should we model the model relation or model similarity in ensemble learning? In the current setting, of course, nobody care about it, right? We just do the averaging or voting or whatever, right? And then, so roll up to the object level. Then we know, okay, so our learning task is to model the similarity between O1 and O2. And then we have to consider the value interactions and feature interactions. And also if you have label, you have the label and the value interaction, label and feature interaction, right? Okay, so that's the overall idea. So on the workout, right? And putting a simple way like this is the same as what we explained already. So you have the intro attributes, value couplings, and the inter attributes, relationship. And if you have label, you could have one label, feature and label relation as well, right? And how to model that? So what we do is that we build a set information function. So basically, if the data can be converted into an information table or extended information table, you have, the label information, you have the model information or model result incorporated into the basic information table just with the object and attributes. And then we can design some information function to extract the value set or the data object set. Value set, it means for given a feature, particular feature J, and for their target object, we can extract their value on this particular feature. And similarly, we can do that for the object level. So given a feature J and a value X, we can find all the objects that satisfy this value, right? And then we can do it for the whole table, for the whole information table. We can use this kind of interaction, information function for individual value, for extracting individual object or object set or value set. And that actually, all this information function, they consist of the information in the data, in the table, and that can be used to build for the learning similarity, etc. Right? So that's what we have. So right, we can actually get the for given the table, we can extract the value, or we can extract the object or object set, etc., etc. And then we can learn the given attribute J, and the value x and y, we can learn the similarity between the value and y within the j attributes or between the j attributes and other attributes, right? And then we combine them together. It's called a into attributes coupling and into attributes coupling. So you put it another way, the into attribute similarity or dissimilarity, and inter attributes similarity or dissimilarity, and then you combine them together. That form into the similarity between two values x and y for the given attribute j, right? And how to do that? So simply give you an example. For example, we calculate for the into attribute, basically value similarity for x and y, and we consider, the value x and y, where do they appear on those, how many times appear in this information table for x and y and they're joined, right? And then we can calculate, the similarity between x and y for this particular j attributes in a function like this. There are other different ways to do as well by considering. So here is basically build on this value co-occurrence, basically value occurrence and value co-occurrence. And then we can, given this table for B1 and B2, we can calculate for this A2 attributes, we can calculate the similarity, right, between B1 and B2. Right, and further, so that's for inter, and then for inter, it means so we calculate the similarity between attributes and x and y for the j attributes by considering other attributes, right? C. So what we do is that, so we borrow the value distance matrix, for the cluster for different, classes for the classification. We convert it into this, modify it for this attributes-based relationship, into attributes similarity. So C refer to other attributes, and then J we want to look at x and y relation by considering the interactions between x and other the value set of other attributes C, right? So mathematically, you can think there are two sets, one centered on x, another centered on y, and each set measure the relationship between x and their other c attributes values, right? And then we actually, what we do here is that it's to consider their dissimilarity between these two sets, and then we can derive to derive and consider whether they have a power set, universal set, or joint set, or intersection set based on the two set relationship. And we can derive, the inter attribute similarity for this full scenario like this, right? So with this, then we can consider, so you may have multiple other attributes, right, k, and then for different k attributes, the relationship between j and each k. So you may see, different attributes may play different role, and then you could have, in a shallow learning way, you could have weight for each k, attributes. But in a deep learning, you could have a self-attention or attention to measure the contribution, right, of the interactions between j and k, right, in order to aggregate the interaction between j and all other attributes, right? So in shallow learning and deep learning, you can also both can be implemented to achieve this idea, right? So overall, if we can learn the inter-attributes relation between for the value similarity and the value similarity by considering the inter-attributes interaction, and then we can combine them over the whole information table to measure the similarity between any two values, right? And that can be for the roll-up to measure the similarity between two objects, ux and y, which hold the value X and Y respectively, right? And so sort of like, you could have a simple way like weighted or whatever, or multiply or weighted sum or averaging, the different ways to roll them up, right? And then we can, with those information functions and the similarity functions, we can develop algorithm. And then given inner, information table, the simple basic information table or extended information table, we can extract the information, basically the interaction within each attribute and between attributes and the label, and then, to measure the object relation, right? And then we can calculate the object, similarity or dissimilarity, and then we can incorporate this similarity into, learning model like a cluster or a clustering method or a classifier, right? And for the user. Right? So then we can compare with the different, existing, like for example, work on the categorical data and compare, this way of considering the more complex hierarchical intro and inter attributes relationship in comparison with like a matching based or other, frequency distribution, etc., and compare the performance. And that's where I show you early on. And in terms of different performance measures, you're going to find actually some of the data actually show significantly, difference between the existing algorithm, the result of existing algorithm, and this way to do it. So which problem means if you have a ground truth, you probably see, they actually haven't really reached the ground truth at all, or actually the result actually are quite misleading if you just use some of the simple way to do it, right? And you should actually often we have to use different measure to evaluate. Because some measure, so you see, even for the last one, it's quite clear in the four measures, looks like, all very, very big difference, right? But in some other measure, you probably see actually, most of the measures or some measures, they actually show more consistent result, but, other measures probably give you a more insight. So to tell you basically, which basically tell us, we have to consider multiple measure to evaluate, because each measure has a particular setting. And by the way, so the measures, they may have some, IID or non-IID idea inbuilt into it as well. So very importantly, but usually we don't consider that, right? We just simply grab it and apply it, right? And then we incorporate that into very basic, like a k-means or spectral clustering, and see the clustering result, and whether the way we introduce could lead to better performance or things like that, right? So that's about the similarity learning. I give you some sort of like a more specific approach in the idea how to model, model the similarity, by considering the value interaction and the feature interaction up to the object interaction. If you look at some of the papers I share on our lab website, you can find actually the many papers we developed in the past years, and actually much more complicated. For example, with the features. So you could even cluster the features, right? So you form feature cluster. And then within each cluster, you build the feature interactions. And then between cluster, there are different ways to build the feature cluster relation, right? So so that's one thing to consider, the hierarchical, but also consider the different distribution related to subspace, right? But in the current or in a traditional subspace learning, you don't really worry too much about that, right? So you have some ways basically to separate the features into subspace, and then you focus on those more useful subspace to do your learning. But how about if the features they interact strongly, in some of the set, and then you probably have to really consider, some sort of like, non-IIDnesses in the features, and then how to model them before you do the subspace, learning. So the second technique I briefly introduced to you, and there are more recent work with another paper published by Chen Zhang, is on the non-IID matrix learning as well. And so these are focused on the matrix learning, and by holding the matrix properties in our design, in the similarity learning. So typically work on the categorical data. The reason is simple, because categorical data has been much intensively explored than the numerical data. Numerical data is much more obvious in some way. And in the categorical data, for example, in this table, you have the commitment high, intermediate, and also the low. What you can see here is that, okay, so you just look at the frequency, H, I, they all appear twice. So if you just simply use like a Hamming or frequency based, you will see, H and I similarity 1, and H and L similarity 1, I and L similarity 1. So basically you see, okay, H and I and L, they are exactly similar, right? So if you consider, simply by use Hamming distance, frequency-based approach to measure, you would get this kind of, conclusion. But we understand, in terms of commitment, high definitely would be different from low, right? And the distance between high and intermediate would be definitely, different from between high and low, right? But how can we measure this in the learning, in the similarity or dissimilarity building? And further, so you got multiple features, and the commitment relationship between H and I, or I and L, etc., could it be affected by the performance, or could it be related to the performance, which means so quite normal. So the commitment affects the performance, right? And then the class, the label, we say, oh, okay, so this is, we give it a high D, or give, let's say it's outstanding or water class or whatever, give a different label. And this label, understand, is related to the commitment, to the performance, individual performance, for example. It could be even related to other factors, right? And how can we also model the relation between the class label and the individual feature? So that's basically what we want to do, basically, to learn the intro feature relation, and also learn the inter-feature relation, as well as the feature and cluster label relation as well in the categorical space, particularly in an unsupervised way. Sorry, here is a supervised way because we have the label. But in another case, if you are interested in the unsupervised way, so you don't have the label, and then how to model that, and that can be used for clustering or for classification. So there's some other papers if you are interested in that. So how to do that? So what we have is that we have the basic problem. There's a categorical data, and which we can do the embedding. Through embedding, so we have the different features describe the objects, and somehow they are separable, or in some way, maybe in a high dimensional way or whatever. And then we can first of all do the embedding. Basically what we do is that with this, we do the kernelization, right? Kernelize, and build a kernel, convert this categorical space to a kernel space. But when we build a kernel space, we actually consider the different interactions I just mentioned, right? And when we build this kernel space, converter kernel space, and then within there, and we can further build a matrix function to measure their similarity and dissimilarity, etc. And then we convert that into a distance space, basically, and then we can measure, and separate the object. Right? So overall, the problem is that also we get, given the observations, for the data, we want to learn matrix space, and want to separate the objects based on what we have learned in the kernel space, in the matrix space. And the matrix space, they follow the matrix 3 matrix properties, right? And then we want to build objective function on top of that, make sure we can actually separate them. That's basically the learning problem. And how to make it. And so we have the categorical data. And for each attribute, and we learn the inter-attributes similarity, as I mentioned earlier. So here you may have different ways to model the inter-attributes. It means like in the commitment data, early on we mentioned, like in commitment, we can measure the frequency-based similarity. That's one way to measure the relationship within commitment. The second way is to measure their semantic relation, right? With high and low, they indicate a different meaning, right? You can have a semantic way to measure their similarity, right? And similarly for performance, you can use if they can be calculated, and then you can measure the distance, or another way you can probably measure the probability, or So that's what I mean. So there could be different ways to measure the value relation within each attribute. And similarly, so between attributes, there could be different ways to measure the between attributes relation. So we broadly call it, inter-attribute coupling, inter-attribute coupling. And similarly, between attributes and class or class label, so you can build multiple coupling function to model the relation between one particular attribute and the label set, right? And then, so here we focus on the kernel method. I use the kernel method because that satisfies the matrix properties, and then we make it easy for us in the distance learning. So, and then we have the heterogeneous, kernel space for the inter and attribute class. Heterogeneous means you have a different kernel, as I'm illustrated for the commitment, right? So in this way, we model the couplings for these three types or three aspects. We model the heterogeneity of different type of relations or different kind of interactions. And we could also model the heterogeneities based on different distribution. It means so the commitment, the distribution, the value distribution could be different from the probability, and we can have different ways to measure, and the distribution would be different, right? Okay, so and overall with them, after learn the couplings and the heterogeneity, and convert that in the matrix space into the distance space, and by involving the prior information and observation here, and then we can build objective function on top of that, right? So that's the overall idea. How to do it? So I'll give you some example. So for intro, we can have a simple way, just give you some example. So we can have the value frequency based. So given the attributes and the value in the attributes, and measure their frequency over the whole, the highest, right? And it's basically converted to sort of like a ratio, right? And then for the intro, and we can measure, so this value VIJ relation interaction with other values of, other values attributes, right? So their value set, right? And when you measure that, it could actually measure in terms of the value co-occurrence in a probabilistic way, or in a ratio, or in some other way, right? And for the attribute class coupling, so it means that we need to measure the value interactions with each class, each label, like C1 or whatever you have in the data, right? To measure their relationship. And you can measure this in terms of the probabilistic way, or in some other way, right? Okay. And with all those different kind of different aspects and different ways to measure the different aspects of relationship, the interactions, and then we can put them together into high-dimensional kernel space. And in each cell, it measures the two aspects of similarity or relation to each matrix. And you can measure the matrix relation for the same or for different. So the diagonals basically for the same. So overall, because we have built the NVG relation matrix, and then we measure basically the matrix relation in the kernel space. And in the kernel space, we can further convert the kernel space into another structure with the diagonal elements only. So that's basically we see by learning the distance between two elements, I and J, and each I and J is converted, to multiple, or is measured by P aspects of couplings, like I illustrated earlier. And we measure the P aspects of distance in the matrix space between I and J, and this in this way, and we can measure the distance between I and J, and then we can convert the original kernel space into this sort of diagonal structure. And here to measure capture the K interactions between the objects, right, and build on the multiple aspects of the couplings, right, and then we can based on the learning problem, and we can build objective function for the K multi aspects, kernelized coupling relation, and your learning task. A learning task is try to separate the objects, right, and J, separate them based on certain settings, for example, the threshold or the bias or whatever. So you follow like a kernel learning approach, and to determine whether you can separate and set up some sort of like a threshold or whatever. And then we can, after we learn these metrics, the similarity, and we can incorporate that into different models, classifiers, even the basic classifier like KN, and then we compare with different distance measures, like other these all other measures, including the basic measure like Hemming. So this is a many data set here, over 20 data set. So what do you have here? With a different data set, as we can see here, is a UCI data set. You can see here some of data are quite simple, like this one, right? So some of them quite simple, but you can also see, some of data they got almost 100% accurate, like a mushroom, right? But there are other data, so all distance measures actually suffer from it, and some of them suffer a lot. Like this one, right? This one, Speckett, quite difficult, right? Quite difficult. So the result is quite low. The F score around 50%. Right? It means the even very simple data in the UCI data, there's still some really complexity there we haven't really captured well. Through this way, we still cannot really capture. But overall, we see after considering this using this new distance measure, overall improvement could be quite significant. And then we do the statistical test with in terms of different similarity measure to see the performance. And here you see the epsilon gamma goodness. You see here actually it's simply the separability would be much stronger than other method. That's why the performance be bigger or be better. And we can further test ablation study to see whether the coupling or combine the coupling and the heterogeneity together, which one make more difference, and see heterogeneity also are important. So it could contribute to averagely 60% of result improvement. And then we can incorporate that into like a logistic regression, random forest, SVM, et cetera, to see the performance. And here basically shows, so with different kind of, learning method, and improvement could be different, right? So some actually could 12% or 9% or 3%, right? So it depends on. So because this is a kernel base, you see SVM is kernel as well. So improvement naturally will be smaller, but other like a logistic regression and a random forest, you see the improvement will be bigger, right? Okay, and that's scalability. Skip it. Okay, so that's the second piece about the machine learning. And let's move to another topic about representation learning. And this is quite topical nowadays, particularly in the deep representation learning. And we actually, there are a lot of work on that. So now I see, in the representation learning, how can we incorporate, the non-ID ideas partially, incorporating full non-IIDness into representation learning is really a very challenging task, but here we give you a little bit idea of how to partially address this issue. The example I'll give you is about the mixed data representation, which basically means you've got a numerical and a categorical data. How can we join to learn the, the relationship, in the categorical numerical data in a deep learning neural network way? Right. So what do we have is that, so you can have, so in the current approach, so like given this example, so you can do the one hot, right? That's a typical way, right? In the NLP and in the categorical data, the event in the modeling in the neural network, you use one hot embedding, encoding. But there are some issues there, right? You can easily say you ignore many things, right? And the distribution or the semantic and the frequency, et cetera, many things has been ignored when you simply use one hot. So really you need to be careful when you use one hot to do the embedding, or simply apply the water to bag or those kind of thing, right? You really need to think about things beyond that. And so for numerical, typically we say, oh, okay, so numerical very simple. So we can actually use some of the numerical distance measures, but hang on. So you have to think about whether you can use that and whether you could do more if the data is more complex. Complex doesn't mean the data is very big. It probably simply means the data is just, complex, but still very, very small, right? But data could be still quite complex. So there are different ways to do that in the neural learning. So in the mixed data, so how do you do it? And think about the way you usually do it. So one simple is that, okay, so I can do the discretization of the numerical data. And then for the categorical data, we can do the one hot or TF-IDF, that kind of thing. And then we can generate embedding in, through the nonlinear activation function, whatever. And then we can combine, basically concatenate them, into one representation, and then throw it into the, deeper layers, and then, to do the prediction, right? So that's a typical way to do it. But I want to remind you, so if you work on it that way, you have to really think about it, but that is really a good way to do it. For example, so in the discretization, so we had a paper a long time ago, actually. So we can't really, if the data, the features, there are feature interaction, different feature interactions, and also the feature distribution, you probably cannot really use a simple way to discretize the data. It could really cause some misleading, incorrect outcome. But if you incorporate, the thinking of heterogeneity and a coupling or interaction, you could actually do a much better job, right? And we also know that TF-IDF, there are issues with TF-IDF, right? So you can't really simply use it in many cases if the data, like an event or in sequence modeling to, or in behavioral analytics. So, so I move to the solution here. So what do we have is that this model we have is an unsupervised way. In the mixed data, we got a categorical data, we got a numerical data as an example. So what I have for each data, each data object is described by numerical and categorical attributes. And then what we do is that we want to have the triple objects here, and then in the plane space, we call plane space, and couple space. In the plane space, we simply do the for the categorical, we do the one hot, and in the numerical, we simply do some distance-based encoding, and then we coconate them together. So in that way, and then we calculate the representation-based distance between the three objects in the representation space, and then in the coupled space, we try to learn the relationship between them, and then for the learn the latent variable, latent representation, and then do some contrast analysis to differentiate them, basically to find, to separate them, basically. But so that's one thing. So we incorporate not only the simple way to do the encoding, etc., but also consider, some sort of like interactions there. So I will explain later. Second important thing is that, so the two learning paths here, right? Two learning paths, one called a P instructor, another called a C instructor, right? In the plane space, in the couple space. What we want to do is that, so in the couple space, what do we learn in the matrix? Some of the learning outcome, learning outcome means here the separability could be converted as an indicator, and that could be used to instruct, the other learner, right? So we do this across, instruction, and in the plane space, we learn the indication of the separability and use that to guide or improve the, couple learning, and similarly we do that in the plane learning. And that actually, shows really interesting result. And how to make it happen? So what we have here is that, okay, so we have objects, three objects, xi and xj, and in the plane space, we just simply do the, encoding. So if it's a numerical, so we do the sort of like you can use some sort of like a distance measure-based encoding through some kernel. In a categorical, you can do the one hot representation, right? And then in this space, so each X here consists of numerical, categorical, multiple features, and then you do this sort of like and then you combine them and build a hidden representation, right? And then you compare the distance, basically compare the distance between two pairs, and so that we can separate, the two pair, right, and see which one, and then you somehow you can get, the similarity and separate, the strongly similar or weakly similar, right, in the plane space. And in a couple space, so what we try to do is that we should see, so there are values, and we consider not only, so here we have the value for categorical and a value for numerical. And a value for categorical, and we can measure the value similarity. For example, so it's categorical, right? So you can measure in terms of multiple ways, for example, like, frequency based, or the co-occurrence, or the, convert that to probability, or if you have text semantic behind, you could even measure that as well, and then combine them together to measure the similarity, right? And between the categorical values. And then for numerical, so you can have some kernel to convert it and compare the, the two value relation, right? And then we combine them together to measure the, the numerical and categorical feature based, the relationship, right? And so that's what is done for the coupled encoding space for different objects. For any object, we can calculate in that way. And then when we get all these, and then we can, for each learner, we have two learners here. For each learner, we can do the, triplet, matrix distance learning for each of them. And then importantly, as I mentioned already, so for this plane learner, we have the indication for the separability. So basically, you see, it's a strongly, you can set something like this, right? You can separate H, basically X, I and J, and through the, the distance, and then you have use this outcome, the delta, as the indicator. It basically shows, which one is strongly similar or weakly similar, and use that as an indicator to inform, another learner. It means, this needed to be considered. So that shows here. So in the plane space, so we have the cover space, separability indicator to be incorporated here to learn, the difference between the two pairs, right? Between the two pairs, basically distant learning. And similarly, we do that for the cover space by incorporating the indicator we can learn from the plane space. And by incorporating this kind of technique, we actually can see, for the user eye data, some of the, data we can actually get interesting results. Actually, if we just use a plain coding or couple them, compare with autoencoder, and in the feature space or in the distance space, and in the k-means or in the DB scan, incorporate that, and you can see actually some of the interesting improvement, and sometimes actually the improvement could be really quite significant, right? By comparing with existing ways, and also you look at the TSNE, you look at the separability here, right? And by considering the hidden features or the matrix distance level, and to see the separability, right? So basically explain to you, why autoencoder perform badly, and in this case we can actually make it stronger and have the separability. Okay. So that's about the representation learning. But if you're interested in that, so there are many papers actually in our lab website on the representation learning, going beyond the typical assumptions or typical practice. That's basically decoupled representation learning. Decouple means, so in the deep neural network, so with the input, so we want to learn the hidden features or learn the classifier that can actually, that are less related to the feature interaction. So basically then you can improve the interpretability by better linking, the prediction outcome to individual feature, right? Because they are decoupled, right? So you can see a lot of similar things in the papers in the past years on the decoupled or disentangled, learning, right? To disentangle, the feature interactions in the neural space, and to improve the explainability and simplify the neural model as well. So there's a question here for you guys to think about. So with a typical like CN, RN, are they non-ID, or do they actually handle the non-IIDness in data? So I think that's a very interesting question to think about if you work on something related to deep learning, right? So another topic I introduce, and then probably have some break after this one. It's about the coupling learning, particularly focus on interaction and relationship. But early on, I think the examples were focus on coupling anyway, right? Focus on interactions, but the target there was to build a similarity, was to build a similarity measure, was to build a matrix, right? And that can, the similarity measure, the matrix measure can be used for whatever learning purpose, But here I give you a little bit more example related to the particular focus on the complex interactions. Give you some example. So, so this one is focused on the heterogeneous couplings, called multiple relation learning for recommender system and apply in recommender system. But overall idea is to learn the multiple interaction. So if you work on the recommender system, so you know the problem, right? So the problem is that we got multiple users and multiple items, and recommendation is that to see to try to analyze the user relationship, and then you see if user US and UT, they are similar, and then you see whatever purchased by UT could be recommended to US, right? So that's from the user perspective. And from item perspective, you look at the similarity between items, And then you see if IS purchased by someone UT, and then you could if US UT somehow similar, and then you could recommend IS to this user, or if there's another new item is similar to IS, I could recommend that new item to UT, right? So there's either item similarity based or user similarity based. And a very traditional idea is to use is called collaborative filtering. Collaborative means you actually look at the neighborhood, look at the similarity between the users or between the items, and based on that you do the recommendation as I just described. But there are significant issues with this kind of settings, actually, this kind of setting. But I want to talk about it here as later in another topic about the non-IID recommended system. I will explain to you a little bit more, but here we just focus on the different relation. So similarly with arrows here, we show there's a user item relation. And we understand there's a users interaction, sometimes directly, sometimes indirectly. And similarly for item, there are item that may belong to the same categories or belong to the same price range or whatever, right? So you can find some way to measure the item similarity or user similarity. So we're broadly called a user relationship, item relation, and a user item relation. So heterogeneous means not only just a user and item, but also there could be multiple different type of relation, right? So with a collaborative idea, so let's say that given a user US and UT, and we can actually, first of all, before we do the recommendation, we actually needed to measure the similarity between US and his or her neighbors, right? Or we probably call it a context, right? So measure the interactions. So for any given user, you can actually measure, the user's, context or neighborhood, right? And similarly for item, you can do that. Given item, you can measure the items, similarity, similar items, and with each item you may have different, context, and that context needed to basically measure the item-item relationship, isn't it? Right? And then further we build the user item relation. It means so I have to measure. So for example, for this UT user and IS item, so what is the relationship we have to measure? But before we do that, before we predict, say or suggest whether IS need to be recommended to UT, we probably can do the similarity between the UT and his or her neighbors, those user, and similarly for item, and then build a way to measure the user and item interaction, and that knowledge learned can then be applied to this particular UT and IT recommendation. So that's the overall idea, right? Okay, so that basically shows how to the main idea. So now let's see how to model that. Okay, so a little bit more mathematical. And here we have, as I mentioned, we have heterogeneous couplings. We have influential context. Influential context means that given a user U, we only highlight those important, influential, users. Called you say there's a context of you, there's a context, right? And similarly for item, so given an item, we can find the influential items related to this particular item, right? And then, so that's the first thing we do. The second thing we do is to model the relation between you and I by considering, their other type of relation, like the use context, the relation between I and the use context, and the relationship between this user U and the item context, right? But of course, you can also measure the context relationship, right, between this and the UUC and the UIC. So this really is the four lines shows four type of relation, hierarchical relation, right? On individual, on a context, and individual context relation. So then overall, the learning problem to learn the multi-relation, hierarchical relation, and become something like this, right? So we have to model there sort of like a score between you and I, a matching score or something. and between you and the I's context, influential context, and between I and U's context, and between the two contexts, right? To form the overall user item interaction score, right? And how do we do that, right? So to measure the user and item score, so we can measure the preference. For example, you can based on data, the click, or the purchase history, you can measure the particular relationship between user and I, right? Or preference between user and I. And for the influential items, so first of all, as I mentioned, you have to build a similarity to find the influential item for users for items. That's very simple. So you can use a KN or some other approach to do it as a starting point. You can have a more complicated way to do it as well, right? And then we can get the representation of UC or IC, right? And then we can model the relevance or the preference of user on the item, or their, or between the two contexts. And not with deep models, and it could be done easily, right? Use attention models, right? Okay. So, so this further shows, the architecture, how to model that. This multiple relationship. So basically what we do is that, as I mentioned, you have a user and a model. We want to build a representation of the user by considering the context, right? Overall for the target user and the influential user embedding. With them, we can aggregate them into user representation by considering sort of like interactions with items. Similarly, we can do that for the item representation, as well as the item's influential context embedding, and aggregate to model their high-level interaction, over this low-level, relationship, right? So that's basically the and in doing that, if this is done in a sequential way, temporal, right, and then it could be involve temporal information. But even without this temporal, this is just handle the contextual information. We still have to consider how to integrate, the individual target user or target item embedding with a context, and that's a key thing, right? So you got the individual user or item embedding, and then their context embedding, and then how to aggregate them. That's becoming a critical challenge, right? So what we do is that, so we want to build the influential context for this particular user. The way we do it is that, so we have the individual, the target, and so we have the target user, ET, and ET has a representation. And then we have the context items. And for context item, we can build their representation and the weighting as well. And then aggregate it, to form their representation here, right? Form their representation by considering their contribution, whatever weight. So that can form into a context representation, right? Contextual representation. And this contextual representation, the next thing I want to do is to integrate or to aggregate, the ET representation and this CT, and that's a key part. So build something called an influential context aggregation unit, and this unit does the job. So how do we do it? So first of all, so with a CT, what do we learn of the CT and the ET? So we have a gate function here to integrate the CT and ET form into a G output, and this G output can be further combined with the CT, right? And this ET can be combined with 1 minus G, and then combine these two together, form into the T's representation in this influential context. So that's basically a function here, so right? So we have CT and ET, we form into a gate, and to learn the joint representation, and that joint representation can be combined through this gate, in this way, and then to form into the influential context embedding. Okay, and then this can be applied to the problem in the recommender system and test on the recommendation data and to see the performance and see whether compare with social relation learning or pure MF or coupling MF or some other and see whether this could improve the normalized DCG or MAP or other measure, right, for top 5 or top 20 recommendation, right? And this photo shows for code star for those new items or new users and the performance of the recommendation for top 5 and for different data set. Okay, and this is we like to see why this works better and to actually find the relationship in the context, right? Okay, so I stop here now, and we probably have a break up to maybe 12:10. During the break, if you have any questions, feel free to send me a chat and or just simply discuss. Okay, do you have any questions? No, okay. No questions. So we have a pause here, and I pause the recording. Okay, so just now I briefly introduced some of technique for similarity learning, matrix learning, and for complex relation and heterogeneity learning. But as you can see, actually, they only partially address some of the non-IID needs. Actually, it's quite a challenge if you want to address, multi aspects of interactions or heterogeneities. Actually, the model become much more complex. So we still have a lot of content to discuss with you guys, and probably need to run a little bit faster. So the first one, I just very briefly touch the pattern mining issue because it's an older topic and there are still some people work on it. But I really focus on the pattern relationship analysis. This is a new topic and new, to the community because very few people work on it and think about it. It's about, how to analyze the pattern relationship. So I just very briefly, so you see, we actually consider multiple patterns. So consider the pattern relation. And for example, so this one, you have a pattern XP associated with a fraud, for example, and then there's another activity happening after XP, and then it become maybe non-fraud, right? So, or in the health medical situation, you see as a medication XP taken, and that's a health condition T1 related to like blood pressure or heart rate or whatever, health condition indicators, for example. And then after another treatment XE, and the health condition may change from T1 to T2, right? So only if we can combine the two together, and then we could find actually some interesting result related to the contribution of XE. For example, we can measure contribution of XE in the traditional frequentist framework, or we can actually consider some like PS ratio to measure the contribution of XE to the impact condition on the given or precondition XP, etc., etc. So when we do this, we actually model the multiple patterns and look at their interaction. And this cannot be done by the frequentist because there is a downward closure property. You only, only enter in, the high level patterns, and all the subtle will be ignored. And this photo give you an idea about a cluster patterns actually. So you can look at a global pattern, look at the, the whole change and evolution, and then not only the evolution of the patterns, but also the impact or consequence, and then you can model that. And we can use that. We build this for the some of the project we did, like look at a cluster pattern with the customer circumstance, like at 65 years old, and then the government policy, and then the customer feedback, and then risk level. So you see here actually this is a cluster pattern, but then you further decompose and involve multiple parties as well, right? Okay, so if you are interested in that, you can look at some of the reference, talk about the implicit rules or pattern relationship, and this is still quite relevant in the current context, especially for enterprise learning. In the big organization like a bank, typically they use many rules, and then you have to look at the rule interactions, and then so to reduce the false positive rate and the low detection rate. So and now I move to another topic related to statistical learning, but I put a non-IID here is actually just to partially address it, to be honest, because there's statistical learning, there's some very strict, conditions there and settings applied. I will explain to you. And give you an example is still recommended system. It's easy to interpret and widely applied. And here what we have is that we have the rating and the missing rating, and we have the user relationship, and we have the item actually or user relation, user attributes, and the values. So there's a three sources of data basically, right? So what you can see here is that you got multiple type of information or relationship. Number one. Number two is that you look at the sparsity actually quite different, right? So across these like good fellows, so you see here there's a sparsity mainly here, the full high sparsity, but the value actually very consistent of 5. But in this case, more like still you got a less sparsity, but the value is also same. But here you see they're different, 5 and or 1. So you see here the distribution quite different. Number one. Number two, the sparsity also different, and also the sparsity distribution also different, right? And so this is, we just look at the rating data, but before that look at the user metadata and the relationship. There's sort of a similar kind of non-IIDness there as well. So in the and consider this in statistical model is quite challenging. And by the way, in the statistical model we have the basic Bayesian rules, and I assume all of you know that. And then in the Bayesian probability model, we have very, very fundamental things called, we assume all the samples are ID drawing from the data, and on the same prior. Right, as also we see, the data is changeable basically. So with that, and we can build a hierarchical model with a conjugacy there, like this theta actually conditional on another alpha and alpha t minus 1, etc., etc. There's a hierarchical model also in the deep Bayesian, we call it deep Bayesian networks, but follow the frequencies, follow the Bayesian framework, right? So you can have a hierarchical model like this, gamma, and Poisson, for example. And in the Bayesian inference, so the very, very fundamental thing is that SVI, the stochastic variational inference. So with the observation, and then we assume there's a local variable Zn and a global variable beta that are influence this xn, right? And then we can build probabilistic model like condition on the prior alpha like this, and this can be factorized conditional on the ID assumption into this way, right? So this was what we basically do, right? And so the overall is that is to learn the posterior, and by involving the local independence, and also because of local independence, then we this one would not be related or somehow too much dependent on the previous. And the second thing is that we have another ID assumption here, so that we can factorize it in this way, right? And then there's another thing that conjugacy. So basically, so you're in the same conjugate family, basically. And then to resolve the inference, so we typically use ABL. So ABL is that to learn, so this joint probability can be further converted to the KL divergence, and maximize the KL divergence is equivalent to minimize the ABL basically. So then the difficult problem of to solve this probability posterior can be converted to a KL divergence optimization issue, right? So that's what you do in the Bayesian network or the variational neural model, like a variational autoencoder, etc., etc. It's a very, very fundamental thing there. And here we just introduce one example here for the large scale sparse and multi-source data. So focus on the user item sparsity and also the dynamic and dynamic. Dynamic in statistics means have infinite parameters basically, and how to learn the parameter, right? So what do we have is that we have rating, user rate on items, and at particular rates, right? So that's basically the Raman system. We want to estimate the rate, and so that's basically the learning problem. And now, in the statistical model, what we do is that so assume the rate can be factorized into user latent feature and item latent feature, theta and beta. And here, this line, the left hierarchy refer to the user hierarchical interactions and hierarchical factors, and the right path refer to the item, basically. So then we assume the user latent feature is affected by user preference or behavior, which also influenced by the user attributes, and similarly we can have similar assumption for the item as well. And when we build the statistical model, we have to have this the conjugacy hold between these hierarchical variables. So then the model we build by incorporating the user attributes, what do we call metadata, and then we can have for the user attributes, we assume it follow a gamma distribution with the shape and rate, and these the item attributes we can have similar one as well, and then for the next step with user attributes HUM, and then we build that into the user latent behavior. And the user latent behavior, you see here, the rate is actually accumulated based on the user attributes basically, and similarly we can do that for the item as well. And then the factorize is that, so we assume the user latent preference and items latent feature follow gamma distribution build on their user latent behavior and item attractiveness, and that can be combined, compensating to by Poisson to estimate the rating. So that's a generative process for the hierarchical model, this hierarchical model, right? So when we do that, so there are local, these are local factors and local variables, but the number of variables to determine. Then basically you see you can try different k and then get the value and then see, just like a MF, right? Matrix factorization with a different dimensionality, you get a different result. But that could be quite unstable somehow and uncertain sometimes. And what we can do is that another model is to incorporate infinity into it. So what we do is that, so with a user latent preference or item attractiveness, and so you've got a k latent variables. We want to automatically determine the k, of course, optimal. And what we do is that we incorporate extra auxiliary variable between the user preference and behavior, and this one, and we incorporate a non-parametric Bayesian approach to optimize and automatically determine the k. So by incorporating this auxiliary and also a non-parametric Bayesian technique to determine the k automatically. Right. So and a similar generative process for the user attributes and item attributes. But the only difference here is that so after the latent behavior assumptions, so we incorporate auxiliary variable, and which actually, you know, this variable follow stick breaking process in the non-parametric Bayesian. So basically determine the stick breaking probability follow a beta distribution. And then the user's latent preference can measure not only by their behavioral inference, but also the stick breaking probability for two parts, right? And this will be further incorporated into the factorization, Poisson factorization. But here, because we have when we do this, we extend it to infinity, right? It's a k, and then we can use a model to determine the best k, basically, right? And then to solve this problem, so we have the variation inference, so which basically means that we got all the latent parameters, and we factorize to the latent factor and their auxiliary or you know parameters, and those auxiliary parameters or called variation parameters. And when we do this, a very important assumption is that we assume, you know, those factors, latent factors, they are independent, right? When they are independent, and then we use a mean field, you know, and we factorize it in this way, right? So this is very important. But how about, or what if the variables, they are independent or they are non-ID? And then this could not be done, right? And this could cause a very big trouble to the probabilistic graphical models or non-parametric Bayesian as well. And basically, same for VAE, variation autoencoder, it couldn't be done, basically, right? And similarly, when we have the stick breaking process incorporated into it. So by the way, stick breaking process is widely used in non-parametric Bayesian, like Chinese restaurant process or India buffet process, if you are familiar with that. So you have this, and then because we incorporate that, then, you know, there's infinity there, right? So you get an additional incorporating into that. So that's basically, you know, a little bit different from the previous inference model, right? Similar here. So if the variables, the hierarchical variables, they are not independent, and then I think, you know, it will be really big challenge, and nowadays still cannot be cracked by the statistical community, and that's why it's still, you know, very challenging for statistical model, even with SVI, and we can extend it to larger scale with GPU sampling, but still, I think, you know, the performance still not compatible with neural model in a lot of ways, even though the explainability is much better. That's why I think it's like a way is to combine the statistical principles with a neural computation and to enhance, you know, and to integrate. Okay, so then we apply that on the large data and to see, you know, on the performance. So you see how in the statistical performance, you know, by considering the metadata and metadata relationship. Number two, by incorporating the hierarchical relation, more hierarchical relation, performance could be substantially improved, right? So the bottom two represent that. And then with the non-parametric Bayesian incorporated, that can actually optimize to get the best latent component and compare with you know, the one without the non-parametric, that actually you have to try different k latent variables in the graphical model, and that you know, lead to different performance, right? So if you are familiar with that, so that's basically the case in the data. And then when we test actually with hierarchical conditional property factorization or other models, and see whether that model we develop can actually focus on the sparsity, and those cold star or sparse data can be highlighted here, can be better treated. So that means that we can actually better look up at those disadvantaged or those new use of new items, right, in this way. Okay, so next move to the non-ID recommender system, and recommender system is so popular, and seeing so many people, to start with non-recommender system because it's simple, it's easy, and easy to get data, and very useful as well. But here I focus on non-ID and the non-IIDness into the recommender system. I will ignore that too with like a collaborative filtering. Those approaches could cause big problems. Give you an example in Google. So in Google News, there's a news here about violence happening in Greece some years ago, and there's a picture here. And then they have a recommendation for the recommended advertise here, and shows there's some very beautiful beach in Greece, and encourage people to go there. So the challenge here is that if someone follow this Google advertisement and go to that beach, but because of the violence there, and this guy, was somehow harmed, during the traveling, and could he or she sue Google because of this? So what I see here is that if this ad is automatically matched between this, of course, this is totally challenging, right? So this is not a good job done, right? But why this happened, right? So I think you can think about many reasons. Think about we have to look at the image, do the image analysis, and the news article NLP analysis, and also the ad, and look at their interaction, their relationship, and their heterogeneity, and altogether do a much better recommendation probably. And simply, so with recommender system, I summarize it in this way. So you basically, usually we just work on the rating table, right? The user rate items rating table. There's a missing item, missing rating, we can do the estimation, right? So that's a major task. And then we actually have the user table, also have the item table. And I add a fourth table, that's a hidden table, is the interaction between the user attributes like a city and item attributes like price, right? So it's the interaction between those, user item attributes. And importantly, as we know, the user attributes, they follow different distribution, similarly for items, and they are heterogeneous, right? And by the way, so when you look at the rating pair, do you think is this ID or non-ID, or could you incorporate non-ID into the rating, right? So if you have millions of users, and likely the rating will follow some sort of like a non-ID, right? But of course, in the current recommender system, nobody care about that, right? Okay, so with this table, then we see the rating made by user on an item could be interpreted by the interactions between all the ratings made by U1, and probably the rating behavior of U2, U3, the inference of rating behavior U2, U3 on U1 some way. So that means in the simple rating table, we can consider horizontal and vertical interactions and inference, right? But even if it is an example I mentioned, very large scale data rating table, and there could be multiple distribution there, it means that, as I show Ollie in that statistical learning shows actually the rating distribution quite different, the spotting quite different. It means we need to have different model. So in the statistical model, you can actually somehow cope with that, because you can have some sort of like assumption to model that. Okay, and then this rating file is influenced or may be influenced by the user table. And user table, there's a user interaction that's built on the within attributes interaction or between attribute interaction, and similarly for item, right? And then another one is between the user item. There's a sort of like a more latent or hidden relation between the user item. Typically, people do not worry too much because it's more direct, right? Between user and rating, item and rating. That's called a user or item based, collaborative filtering, or et cetera, et cetera. But why do we not consider the interaction between user and item in their attribute space and consider their influence on the rating behavior, right? So I think this diagram basically cover a lot of most of probably the topics in the Riemann system. And importantly, I want to emphasize that we will do that. We'll consider user non-IIDness item and user non-item interaction, user non-item feature space. But as I mentioned earlier, even the rating could be non-IIDness there as well, but usually it will be ignored. And further, so if you work in Riemann system, you probably see actually I group all different topics in Riemann system into this table, and multiple generation from the first generation rating focused, and then you incorporate some social relationship called collaborative filtering group or social recommendation, and then you cross domain, more focus on item, right, and group recommendation for items, etc. And then much less work on really, the fourth table, right? And there are other environment related, so if we Riemann house in Australia, in Sydney, could be very different from Canberra, right? So the environment actually quite important as well. So there are interactions there as well, right? And if you incorporate their heterogeneity there, or their different sorts of hierarchical relationship, and that could be quite interesting. So a lot of work actually on that. So I just give you maybe, let's see, one example. So a very typical thing is to use MF. I still see some of the papers really just work on the non-negative, MF to do the recommendation. That's very simple, right? Because you have a rating table with missing value. What you do is that you factorize it into two latent user space and item space, and then you basically assume they multiply and then can estimate, right? So this is a mathematical model, basically, right? But if the rating, for example, is the same rating, same missing, but one for a house in Sydney, another maybe a house in London, for example. So if you use, let's say if we use MF, we would get the same result. The only difference is that you manipulate the dimensionality, right? With different dimensionality, of course, the result could be different. But with the same dimensionality, you would have always the same result. But does that really make sense? Because in Sydney and London, the price, those are very high, but the market condition, the people's preference could be quite different, right? So this way of estimating the missing value in terms of factorization of this, the latent user vector and item factor, that's probably just too mathematical, right? If we do that in the real case for the Riemann system, we really need to consider user and item, and that's what I call user coupling or item coupling, and that built on the very first similarity learning technique I introduced. So you have user. So with the user, you have multiple user attributes, and then we can consider the value similarity for each attributes and between attributes, called intro attributes or inter attributes, and then you roll them up, integrate, and build the user relationship or user similarity. Similarly, we can do that for the item, right? And then we can build a very different, so that's about how to learn that. So you can have different way to learn it. And then in this MF, we will go far beyond the simple MF model, right? So rating can be estimated by user matrix and multiply item matrix, and you then have to go far beyond. The rating matrix is just one thing, but we actually needed to learn the user coupling, item coupling, and then incorporate that into the MF for the rating matrix, right? And then we can build an objective function library. You can still do the estimation based on the ground truth, but to that we have the P and Q. We have to consider, the user latent matrix and the item matrix that could be affected by the neighborhood user, for example, or neighborhood item. Right, but you can also have other way. It's built on some other relationship. So here, for example, if you consider the user U is somehow influenced by the context or by the similar users, right? So that's a simple example to incorporate the user relationship or ID relationship, and then you can resolve it through the gradient descent, right? Okay. So here shows that to compare with a probabilistic or the social relation related or SVT based. So you can see actually you could make, sometimes you could make a significant difference, improvement, and sometimes you could make a very minor improvement. And this is sensitive to the dimensionality, right? Okay. And compare with a user or item based CMF only, right? Okay. So that's another example, shows the result. Anyway, just ignore it. So there are other ways, a minute actually. So just a very brief here, like this one. So you in the next item recommendation. So you can consider. So basically, you have item and context, and then you can build the hidden representation. And by using tangent and stuff like that, so it's quite simple. You can do it in a more advanced way now. And this one actually shows another example. So you see, okay, so with a collaborative in a deep neural model, so what we can do is that we can actually have the very simple user item, user one hot, and build embedding for each user, each item, and to measure their user item interaction in the latent space. Basically, use a one hot embedding, and then in the neural model. But we can do it. We can have another one. It's based on user information on item table, and we can learn the sort of like a kernelized relationship between the users, between items, based on their value and attribute value and values, right? And then we build a user item coupling, what I call it, and then we combine these two together. And there are different ways you can combine them. You can also have a gate, coupled gate. I will introduce another one later. And then, before you put into a predictor, right? So, and this shows actually could make some significant improvement as well, right? And in another example, just very briefly, so you see, if there's like a user to watch some movie and with some actor information and also some statement about the movie, right? So you got a text here, text data. You go to the movie, the actor or cast group, the individual members, and how can we learn, why this movie is more attractive to this user than others? So there could be some reason to model the attraction, right? Or could attraction modeling. So in doing the attraction modeling, very important thing is that we have a user, and then we consider the learn. So given a user, we learn the user representation that's sensitive to their actors or actress, right? Okay, to learn that, right? And similarly, so we give the user, in order to learn the user's interest in the words, right? User's representation in terms of their words from their movie statement. And then how do we learn both of them? So we can roll up to the group, the cast, and to the sentence, word to sentence, and to the whole story, right? Before we build a user and item interaction. So that's basically shows here also how to build that, right? So so this is quite a interesting, right? So you consider user and two sources of data, and also in a hierarchical way to model the relationship, right? Okay. Anyway, so I just because of time issues, I can only just very briefly introduce them. Now I move to another topic called behavior analytics, and nowadays behavioral AI becoming more and more recognized, and behavioral informatics, behavioral computing become much more recognized than before. So there's a website if you are interested, a lot of work related to that. So first of all, I focus on how the coupled and group behavior, collective behavior, like in the traffic. You think about it, why there's a car accident happen, and that caused a lot of problem. Probably because the cars all covered and under the road condition, right? And how to model this kind of thing. In modeling that, we have to model really the multi-party, multi-correlation, multi-lane, etc., right? And simply, so so in the paper here, so we actually discuss about could we actually generate abstract behavior model and capture the subject, object, and action, place, time, etc., about this behavior, and then you got multiple behavior, and they're all related, and then form into for each behavior we have multi factor behavioral representation. Basically is a vector, right? And then for multiple behaviors, for each behavior is a vector, and then you got multiple sequential behavior or temporal behavior, and then you got a behavior vector-based behavior representation. And with that, so whether we can incorporate into some of the model. For example, for pool manipulation in stock market, basically a group of people, they try to interact and somehow on a table and manipulate the stock price and push the price up, and then they can take advantage. That's basically. So, but if you just look at the trading engine, look at the transaction, you cannot really find the relationship, right? So what we do is that I will see, look at, okay, so we got an investor 1, 2, 3, 4, 5, and look at their buy or sell, and then try to model their relationship similarity or relation between them, and then to find a group. They actually collaborate, and then they manipulate the stock. To do that, so we actually have to after we have this for each behavior, build the behavior representation as a multidimensional vector, and then with each multidimensional vector here, each cell refer to element refer to a multidimensional vector, and then each row related to one investor's behavior at different time window, different time point, and then vertically we refer to multiple traders, right? So we have to measure the relationship within the trader, right, or the investor, the behavior relationship. So to model a relation between the behaviors of the same investor, right? And then we have to model also the vertical relation, which basically means the relations between the behavior at the same time or same time window from different traders, investors, and then combine them together. Basically, combine them together to model not only the within behavior and between behavior. I mean, within the trader and between trader behavior, and then group them together and build an objective function to model this, the horizontal and vertical relation, basically. So in the by the way, in the transaction data, so it is not really behavior oriented, right? So you have to convert it, and that's what I mean. We have to build this matrix, build a behavior matrix. But anyway, if you are interested in that, there's a talk tutorial there as well. So with the trading behavior transaction, so we can build a trader sequence, and each element here is a multidimensional vector, and sell and for trade as well, buy, sell, trade. And then we need to model the relationship within each sequence and between sequence. That's a KC, right? And each element is a high dimensional, like price, volume, etc., etc. How to do that? So we have different ways. One way is that we can incorporate coupled hidden Markov model to model the trader states and sell states and or buy behavior at a different time with corresponding different state and observation related to price and volume, etc., etc. And then they influence each other, right? And there's a state transition from T-1 buy to T buy and T plus buy, and this could affect the next moment sell or trade, right? So how to model that? So here's coupled hidden Markov model, and map the category, like the state different buy sell trade to the state in the coupled hidden Markov model, and then the observations to the state representation, and then there's a coupling between that. So there's a few parameters in the coupled hidden Markov model. Right. So all the details, very, very much details you can find in the KDD paper or TKD paper if you are interested in that. And then we can also build their relational properties tree or other statistical model, probabilistic model, like a relational Bayesian classifier to model the trade, sell, and buy. And for example, so we can have for each transaction, could it be buy or sell trade, and we can actually have relational features, latent feature, of course, and to model that and use conditional probability distribution or stuff like that to model, the inference of those latent relational factor on this particular, trade, right? And model that and see the performance, and then find those, more relevant, traders as a group to manipulate stock. So this one I'll quickly introduce another interesting work and also very useful in industry, but very hard to model. It's called a next best action in the multi-party interactions. So this is quite particularly if you do it in a personalized way, it's very, very difficult. So the problem is that, so you got like a client and a decision maker, for example, like, client of CPA, and then you got a CPA here. Or ATO, the taxpayers and ATO government. So what I have is that we got the customer demographic and customer behavior. And the customer behavior usually is a response to the government or to the CPA, right? Your CPA, I'll give you a data example. For example, so if the customer overclaim tax, and then the ATO will identify, flag, and then, contact the taxpayer and send a reminder letter or something like that, right? And then there's the interaction, right? Interaction between ATO and taxpayer. And then the interaction may change the previous state. For example, there's a debt, $10,000 in debt. And then after interaction, so hopefully after interaction, the data could be changed from 10,000 maybe to none or lower through some arrangement, right? And that happens actually everywhere, in terms of multiple party interaction. The challenge here is that how can we model the interaction between ATO and the customer and model them in a sequential, dynamic way, and model them in a personalized way? It means for individual customer. So this is quite a challenge. And then another thing is that at a particular time point, can we actually recommend the best action to be taken on this particular customer? So that's a problem. So it's quite a challenge. And the way we do is to incorporate reinforcement learning with behavioral modeling in the deep neural network. And the overall problem is that, so we build a reward, and then see there's a domain-driven reward given by, for example, by CPA, and then there's an estimated reward of the action, the best action to be taken, and then we measure whether we can actually optimize the reward of our recommendation on those actions, optimal actions under the particular customer's circumstance, CT. So that's a problem. And we do it by integrating, reinforcement learning rather than just based on reinforcement learning, because in the reinforcement learning is just on the reward for optimizing the strategy action, right? And so if you know that there's a value function there, but here we actually consider in MBA next best action settings by considering the customer circumstance and the action. How to do that? So with given a customer, there's a customer's circumstance, so we can build a representation for that, and then we learn a state of that customer, and then for action or candidate action, we'll build a action representation, and then we want to focus on learning, the interactions between the customer state and the action. Particularly is that, okay, so there's some action taking on a customer, and our customer has some response, and then for the change the state and over time, and we want to model their interaction and then build a reward and use a reward to optimize the actions, and then we call it best action, and then at a particular time point we can have the next best action to be recommended. So that's basically the idea. Okay, how to make that? So basically we have the customer demographic through some representation learning, and then we build, the representation of customer, and then for the given input data, so we have their representation that's based on the input data, and then for the action from the decision maker, and we build an action representation, and then the action will be interact, with actions over time, right? So that's basically like a recurrent neural network in the superhuman modeling. And here the response actually, is a response to the action, right? So the response, build a response representation that actually responds to action taken by the decision maker or service provider, and that actually for the inference and next response, right? So this is more implicit in the hidden space, and these two combine together to build representation of the customer for each particular moment. And how to model the interaction between the customer response and the decision action. And this is quite important, right? It's the most important thing here, actually. So what we do is that we have the customer response, so a different time point, and it's a current and historical. And similarly, we have the action historical and the current, right? So build called a coupled recurrent unit. So what we have is that we have the set, update set, and reset gate, and update gate, and also interaction gate. So basically, so for customer response, we have the reset and update, and for the action, we have same thing arranged. And then build the interaction. So way to build is that, so first of all, for the actions, we can have their update, say, for the previously identified the best actions and the current action to be chosen or to be evaluated, and build a representation for updating. And then we can have updated history. Update the history based on the previous good ones and the current updated, and then we based on all these, the action, the current action, historical, and then we can actually update the current action we evaluated, right? Evaluated, and then we combine to evaluate the best action, by combining. The current one with the update and the previous best with the historical, basically. And similarly, we can do that for the response, and then we combine them together, interact through this interaction gate, basically cover them, basically, right? And so that's called a recurrent. And then we can model the customer's historical or their demographic information, as well as the states and the action applied on that to build the representation of the customer, and then incorporate that into for the deep neural network for reward prediction. So, and then we can find the optimal action and estimate the average reward, and whether the average reward can beat what are given by other models, including deep models and LSTM or the GRU, etc., and see the improvements of this way in modeling multi-party interaction over time, and look at the arrow MSE and see whether we can actually substantially improve it. Okay, so next we just very, very briefly introduce one related to vision learning by incorporating some sort of like a non-IID ideas in the image. So a POI, the region of interest, and region can be further decomposed in the cell, and in the cell form a cell graph, and in the region form region graph. And what we want to do is that, so in the cell and the region level, so can we actually model or capture the multi-aspect representation? Hopefully we can leverage the weakness of individual, and then jointly learn that in a metric space and for the segmentation, right? So the way to do is that, so we go to the graph, cell or region graph, and then we can learn their representations through like a direct product or hostile distance or matrix max pooling or something like that. So now that you can have even more advanced ways. And but when we model each of them, we consider both intro and inter. It means that so we have 2 points, right? X or 2 sample xi and xj. We consider their interaction in terms of direct interaction between xi and xj, as well as interactions of xi and j condition on their neighbor mj and mi of the I neighbor, j neighbor. And similarly, we do that for other representation, and then try to incorporate that into a kernel objective function. And for the pairwise and for triplet, so if it's unsupervised, you can do the triplet, right? Okay, and then build the objective function and see whether the performance of by incorporating them, intro and interway, and also combine them could substantially improve the performance over the baseline and lead to better segmentation performance compared to other approach, right? Okay, so that's very brief. So there are also, of course, you can find a lot of relevant work actually somehow incorporating the more relationship or heterogeneity into the visual. So next big topic is about non-IID alternate detection. This is a big topic because it has been here for dozens of years, and it has it's an older topic, and it's very broad and very useful and widely used. And now there's need more to deep alternate detection in a way. So here, we particularly focus on the idea of how to incorporate non-IIDs into alternate detection. The problem is that, so give you some example, for example, so you have a data like this, and we can see actually the distribution quite different for each distribution, for each attribute, simply, right? So the distribution quite different. This is basically heterogeneous, and whether they have some sort of like a relationship, and interestingly, so the last column is about the label, cancel or not, right? So here, no cancel, but no cancel, you see here, the attributes of the patient are actually quite divided, right? Very heterogeneous. And how they actually, how can we build a model actually, to couple them with the cancer by considering their heterogeneity, right? And their relationship, because that's basically the problem to work on. And there are different approach in the alternate detection. I just simply ignore that. So important here is that it's what I just mentioned. They are heterogeneous, and they are so very likely, those features they may interact. Why? Give you an example. So, for example, for the typical problem like diabetes, the typical 4 symptoms that you see, frequent urination or weight loss or lack of energy or excess thirst. There's 4 typical symptoms. But if you look at their distribution, they're quite different, right? You look at their distribution, very different. So heterogeneity, very simple, very clear, right? And some of the things, so if you look at the, look at the not only distribution different, but also you probably can also look at, if you look at the correlation or pairwise, you can also find some sort of like a relation actually quite different, right? And it means, so if I only have one symptom here, it may not really mean I have diabetes, right? It means you have multiple features probably somehow coupled in some way, right? How to model that? Right. So here I briefly introduce some of the technique. The first one is that see whether model the value heterogeneity and model the value coupling as well. So the way to do is that, so as an example I show, okay. So in the alternate detection, because it's very different from the classification, so the thinking is just the opposite. So the key thing here is that it's model the alternateness of value and the value co-occurrence or value relation with other values, if you like. So it's something called a co-current concurrent outlier behavior, right? And give the data. So we want to model the inter-feature and inter-feature outlier factors. And then we combine into value outlierness and use the value outlierness. We can do the feature selection or feature weighting. But of course, we can, with the value outlierness, we can directly do the outlier detection. But we can also add another step to the feature selection and then build an outlier detector, right? So that's the overall idea. So the difference from the traditional approach is that we actually focus on the intro and inter feature interactions and how to model that from the outlying perspective, and then combine them, to do the feature selection or to do the outlier design. And to model the intro, because as I said, is here we focus on outlying behavior. So what we do is that we can build, since it's just an example, you could have different ways to do it anyway. So you see, given a value, so we have the because the categorical data here we'll focus on. So we have the mode for we can have base mode, and then we can have the duration. Duration matters, the mode frequency and the particular value of frequency. The difference between that, in this mode condition, right? And then we can measure the duration, and use this we can calculate the value outlierness in this particular feature, right? And then we can further build the intro feature outlying factors, and by considering the interaction between you and other ways and my target and other value, and this value from other feature, basically, right? So the V value and the interaction between U and V and W and V from other features, and to measure this inter-feature outlying factor. And with that, we can convert the problem into a value graph. So the same color, the value, categorical value from the same attributes, and then the interaction between the values from other attributes, and within we would ignore because we measure that intro already. So build that value graph, and then we can build algorithm to do the search, basically. So something like a random walk, and then we can find the outlying value, right? So and build a detector, and of course you can also do that with the intro feature and inter feature outlierness combined. You can actually do what? You can do the feature selection, right? Because you can measure the feature outlierness and then do the feature selection, right? And then we can compare with typical probabilistic models or other NLP-based information theory-based models, etc., and then compare the performance and improvement over them. So you can see some of them could significantly improve the performance, right? And you can do if you add the feature selection and see whether the performance. So typically, of course, in some of the data, we have to use that. And this is the second paper, just quickly illustrate how the features actually selection could make a difference. So with categorical data like this, so you got some of the noise feature, relevant feature. Relevance means, because there's a low here, is more likely relevant to yes, the cheat or not, the fraud or not. But here must looks like it's a noise feature because it has no clear relation with the cheat. Right? So this is a noise feature, and this is a more relevant feature. And when we do the feature engineering, we have to consider the relationship and the heterogeneity, and that's sort of like the thinking of non-ID to incorporate into the feature selection or feature engineering, right? So how to incorporate that? So the way this is unsupervised. So what we do is that we're going to given the data. So we do step by step and in an iterative way, and we measure the feature value to feature outlierness, and with that we can get the outlying score. And outlying score, we can do the ranking, and after doing the ranking, we can select the feature subspace and iterate this process and up to find the optimal outlying ranking, right? So that's idea, iterative way to do unsupervised way, and consider the co-current outlying behavior as well as a randomly co-current noise behavior, and then remove that and can actually build that into interpret that into a graph as well. So here there's how to model the what do we call a homophily coupling for a value way condition on its neighborhood, and then the the interactions between way and other, and in their context of the neighborhood or context, right? And then build an objective function by considering. And what we do is that because it's unsupervised, so we can choose over time, we can choose the top k. Initially start with some random k, and then choose the top k, and then optimize the top k, and then build an objective function by calculating the difference between the selected k and the rest. And in the rest, you can also have some sort of like a statistic, like a median or whatever, and choose some to compare. And basically just try to build an objective function in an unsupervised way, and then use that to build your ordering detector. And then you compare, do the feature selection. So there's a number of samples and the dimensionality, and that's a reduce. So you see some of data, you remove 90% of the features, the performance could still be better than other state-of-the-art other models. And these are all shallow models, by the way, not deep models. Right? So you see, actually, it's so important to analyze the feature. And you can, of course, also compare different feature selection and feature selection by considering more complex heterogeneity and relationship, and look at their performance. So the example shows here is that even very simple UCI data, the performance of a detector could still be quite frustrating. In some of data, you see, some performance not really, some of them not really good, some of them not, still very difficult to, to improve, right? Okay, so there's still a lot of hidden thing, unknown thing we don't know yet. Now, so that's very quick, right? So I now can leave this to Zhilin, and for him to introduce out of distribution detection, and then I will come back to summarize and questions as well. Okay. So I will stop sharing, and Zhilin, you could prepare, and you can share your screen. And at this, during this time, you can, if you have any questions, you can ask. So there's one question here from Chen Chen. You ask for how to determine XE, right? So by the way, which one? Can you remind me? You can unmute you for easy communication. I forgot which XE will. Chen, are you there? So do you want? Yes.
Okay. Hi everyone. I will share advanced research direction named out of distribution with you, and this research direction is strongly related to the non-IID learning. Okay, let's begin. So in the existing machine learning model, we usually assume that the test data is RID, which means that we assume that the test and the training data are dropped from the same distribution, and we call the training data the training sample are in distribution. But this assumption may not hold in practice. I mean, your test data can come from other distribution different from your training distribution, and we call the sample draw from the other distributions are out of distribution samples. Let's see the example. If you train a neural network on the CVAR10 dataset, then you can also evaluate the network on the other dataset, like the SVHN. And your network will also provide some predictions for the test sample from the SVHN. So you want to detect these out or displacement samples and reject the predictions for these test samples. So the target of the out or displacement detection is to identify the test samples that are different from the training data. Like this example, when your training data set is CVAR10, and you want to detect whether the test samples are from the CVAR10 or from the other data sets. In practice, in the out or displacement detection task, we will calculate an out or displacement scores for each test sample and distinguish the in-distribution and out or displacement samples according to the out or distribution scores. And we expect that the out or distribution scores of the in-distribution and the out or distribution samples is large enough so that we can distinguish the two kinds of samples. So how to measure the performance of the out or displacement detection? Actually, we have two widely used metrics. The first one is the AUROC, which is used to measure how large the out or displacement scores between the in-distribution and the out or displacement samples. As I discussed before, we expect that the out or displacement scores between the two kinds of samples are large enough so that we can clearly distinguish the two kinds of samples. And the other metric is the ECE, which is used to measure how well the network's predicted confidence aligns with the observed classification accuracy, which means that we expect that the classification accuracy is the same as the predicted confidence. But we usually use the first metric, AUROC. So this is the very difficult task. Why? Because there are two main reasons. The first one is that we don't have the ground truth. It means that in the training phases, you only have the in-distribution samples, and there are no out or distribution samples available. So you don't know the data characteristics of the out or distribution samples. Because you only have the in-distribution samples in the training phase. And the second second reason is the predictions of your networks are uncertain, which means that maybe your network will provide very high confidence predictions for the out or distribution samples. So that it's hard for you to distinguish the in-distribution and the out or distribution samples. So what's the keys? What are the keys for us to design to attain a good out or detection performance? The first key is that we should obtain the information from your network which is sensitive to the out or distribution samples. So in order to do so, we have to find the essential difference between the in-distribution and the out or distribution samples. According to the difference, the difference of the data characteristics between the two kinds of samples, maybe we can design some methods to find the information which is sensitive to the outer or different samples. So it's very important for us to consider the non-IID correlations between the in-distribution and the outer or distribution samples, because you know that the two kinds of samples are drawn from different distributions. So we have to consider the non-IID correlations. Okay, actually so far there are two kinds of methods to detect outer or distribution samples from different perspectives. The first one is post hoc detection, which means that for a network learn from an in distribution data set, you design a detector for this network without modify the training procedures and the objective function. You don't need to modify a trained network. You only design a detector based on the output from the network to calculate outer or different scores for test sample. And the other kinds of method is to is confidence enhancement. Which means that you want to modify your training procedures and the objective function to make your network more sensitive to the outer or distribution samples, and you expect that your network can provide high confidence predictions for in-distribution samples and low confidence predictions for the outer or distribution samples. For the first kind of method, I show you the baseline method named MSP, and this algorithm is very simple. You can see the equation. This for a pre-trained network learned from an in-distribution data set. This baseline method only use this softmax probability as the outer or distribution scores to detect the outer or distribution samples, which means that for a test sample, this algorithm use this softmax probability as the outer or distribution scores, and then this method distinguish the two kinds of samples according to the gap between the two kinds of samples. Of course, this algorithm assumes that your network will provide high confidence predictions for in-distribution samples and low confidence predictions for the outer or distribution samples. So you can see that this baseline method is pretty easy because it only uses the softmax probability as the outer or distribution score. As an improvement method, the other advanced method improve this baseline method by considering the temperature scaling and the input perturbation. This ODIN method considers the two components for the baseline method. You can see that firstly, this ODIN method considers the temperature scaling for the softmax probabilities, and then for the input, this method do not use the raw input directly. It uses the input perturbated by the adversarial information. You can see the equation. By considering the two components, the algorithm assumes that the output softmax probabilities is more sensitive to the outer or distribution samples. Okay, different from the previous two detectors, this method use another method to calculate the OD score. Firstly, this method calculates the mean and the covariance of the training in different samples. And then for a test sample, this method calculates the Manhattan-Mobius distance according to the means and the covariance. You can see that this method is based on the distance, and the previous two methods are based on the confidence. Okay, different from the previous three methods, I start to show you some methods about how to improve the OOD sensitivity of the network by retraining your network with some strategies. The first one method is called GODIM. This method divides the posterior distribution, I mean the predicted probability, divide this posterior distribution into two parts. And this algorithm assumes that your network will provide high confidence predictions for all the samples because the two parts will be small at the same time. So that's the main reason why your network will provide high confidence prediction for the OOD samples. So this method divides the posterior distribution into the two parts, and then we use this part as the OOD scores to distinguish the in distribution and the out of distribution samples. And the next methods MOS assumes that the OOD detection performance will decrease when the number of classes increase. So according to this assumption, this MOS algorithm divide your data set into several groups according to the concept or the classes. Like if you have many classes, and this algorithm firstly divide this data set into several groups. Like you can use the k-means, or you can know the hierarchical structure of the classes, and then calculate the softmax for each groups for each group. And the next method named OE. This method try to involve the training out of discipline samples in the training phase to improve the OOD sensitivity of your network. You can see that the objective function. The first 10 is the traditional cross entropy, and we enroll some OOD sample in the training phase according to the second term. You can see that the second term calculates the distance of the feature map between the in distribution and the out of distribution samples, and this algorithm try to enlarge the gap between the in distribution and the out of distribution samples. Okay, in practice, maybe it's very hard for us to obtain the OOD sample in the training phase. So this algorithm JCL try to generate OOD samples for the training phase. And the basic idea is to use the GAN model to generate the out of distribution samples close to the boundary of your in distribution samples, and then use the K-out divergence to make the predicted distribution of the generated out of distribution samples close to an uniform distribution. So so that your network will provide very low confident predictions for the out of distribution samples. Okay, let's have a short review. For the out of distribution task, we have two kinds of method. The first kind of method is to design a detector for pre-trained network without modify your training procedure and the objective function. And the first kind of method is to modify the training procedure and the objective function to make your network more sensitive to the OOD samples. And then you should know that the key is to find the non-IID correlations between the in distribution and the out of distribution samples. Based on the non-IID correlation, you can make some basic assumption to reveal the essential difference between the two kinds of samples, and then you based on the non-IID correlation, you can design some insights to improve improve the OOD sensitivities of your networks. Okay, what are the main challenge in this research direction? From my perspective, I think the first challenge is to how to generate OOD samples that are specific to network architectures and the training in different data sets. What does that mean? It means that if you want to introduce OOD samples in the training phase to improve the OOD sensitivity, I believe you have to generate the OOD sample specific to your networks. Maybe you can think that different network architectures and different in discipline training data sets can cross different networks. So different networks should have different OOD samples, right? So the first challenge is how to for a specific network, how to generate the specific OOD samples for the given network to help this given network to improve the OOD sensitivity. And the second challenge is how to balance the OOD detection performance and the in-distribution classification performance. We in this research direction, we mainly focus on how to improve the OOD sensitivity. But usually we have to sacrifice some classification performance, and this is not good because maybe in many in practice it's very important for us to keep a very high classification performance, and then we should we should improve the OOD sensitivity of your network by maintain a very good in discipline classification performance. So it's very hard for us to balance the two kinds of the two performance. So I think it's this is a very very hard research question. And then the last one is how to consider the non-IID data characteristic between the two kinds of samples to improve your OOD sensitivity. I mean, you know that the in-distribution and the out-of-distribution samples are drawn from different distributions, so they are different, and they are and we should find the gap between the two kinds of sample and consider the non-IID characteristic to design the training procedure and and design the objective function to improve your the OD sensitivities. But we can consider and we can consider the non-IID characteristic from many perspectives. Like we can consider it from the input level, and from the value level, and from the structure levels. So what kinds of non-IID characteristics are sensitive to the sensitive to the OD samples? I think we should it's very hard for us to answer this question, but this research question is very challenging. Okay, there's some reference for you to have a deeper understanding about the OD detection direction. The first two papers are good surveys about the OD detection, and the other papers are the popular methods for this research direction. Okay,
Okay, thank you, Zhilin. I think there is a question about, can you explain about the Foster method? Is this related to Zhilin's talk about the Foster OD?
So, okay, this method is the baseline method of OD detection. So you can see that for the classification task, we usually use the cross entropy as the loss function for our network, right? So this method use the output confidence to use as the OD scores for the test samples. Like, so the basic assumption for this method is that your network will provide very high confidence predictions for the in-distribution samples, and will provide low confidence predictions for the out-of-distribution samples. So based on this basic assumption, this method uses the softmax probability as the OD score to distinguish the two kinds of samples.
Okay, so any more questions for Zhilin? Okay, so if no more questions, so I come back to my presentation then. Okay, so thank you, Zhilin. So I think what Zhilin just explained, I think related to some particular non-IID aspects. Let me put it in that way if I understand correctly. So particularly the OD focus on the distribution, of course, is D, right? Distribution. And then you focus on, so I think in two different settings. One is that just in the training data, so you have two different type of setting distribution. One is more related to classification, another is more like a noise, right? A noise to the learning task. So that's one way to understand the OD. I guess, Zhilin, you can correct me if I'm wrong. The second is that it's really in the learning process. Is when we split the data into the training and the testing. So that's typically called in sample and out of sample. And then in the in sample, you have a given ID in distribution. And then in the out of sample, you have OD, out of distribution. It means in the test, so the model trained cannot really differentiate those out of samples in the out of distribution samples in the test stage. But I realize, I think what Zhilin discussed here mainly refer to the to those OD samples in the in distribution. So in that way, I think it's somehow similar to noise feature, in detection in the feature engineering. Or we see the noise distribution in the training set, right? But that's some sort of like understanding. Of course, I think probably more challenge is that after you train the data, you assume the training is fair and is sound, but in the test data, because of whatever reason, the data, even the same object from the same object, but their behavior has been changed, or their some of the attributes or dynamics have changed. Then how can we sort of like have test stage, as a test stage, we can have a pre-trained model to be more robust for the changing data. And that is, from that perspective, I think in the non-sampling based stage, I mean training and test splitting setting. So I think that's common, right? In topics like active learning, online stream learning, those adaptive learning, domain adaptation, etc., etc. And that's where we actually handle some sort of like a change, deviation, etc., right? In the either from the distribution perspective or from other perspective. And also the other relevant topic will be like you have some more noise distribution or noisy feature, right? So how to make the model more adaptive. But in his case, I mean, in the OD case, or the Zhilin introduced here, I think more related to the deep neural network that is in the training stage, if I understand correctly. Zhilin, feel free to clarify if you think some misinterpretation. Zhilin, are you okay? Okay.
Okay.
Go ahead. Do you want to add something?
You mean the challenges or the challenges of the with saturation?
No. Okay, don't worry then. So I mean my comments. Anyway, so maybe we'll come back to the discussion later. And thank you, Zhilin. So I now move to the conclusion and also the some of the opportunities and directions related to this more broadly. First of all, so what I have here summarized to you actually is this diagram. So this is high level, highly summarized diagram with a given learning problem, whether we have the IID needs or the non-IID needs incorporated into our learning process, learning model, or learning preparation, or the learning evaluation, right? So at a different stage, we could incorporate the IID needs in it. For example, in the feature engineering, so if we incorporate the IID needs, then basically assume those features are IID, right? And then if there's a strong feature interaction, it would not work well. So that's for the feature engineering stage. In the modeling stage, if we assume the value, attributes, the object, or the data source, or the modality, or domain, or whatever, if they are IID, and then the model may have some problem. And in the data part, if we do the data splitting like a training or test, if we don't do it properly, like what I show in the cross validation, or then the result may not be really solid. And then in the model part, in the case if you have multiple models, like an ensemble, and then if we simply do the averaging, voting, etc., and that may cause some problem. Similarly, in some case in the evaluation, if the measures or the evaluation metrics, there are some sort of like relationship there. And then we probably have to really consider their relationship, even though I think many of the aspects or comments I just raised may not really, or may haven't been really paid much attention in the learning or analytical community. And this reflect the bottom line C diagram and show. So how can we actually learn the interactions or the couplings strongly, weakly, explicitly, implicitly, locally, globally, etc., dynamically, statically, etc., and also the heterogeneity from data type, distribution, relation, the rank, the order, etc., right? So that's what I mean non-IIDs. I think with what I like to share is that if some of you are interested in that, so you probably can further think more about this kind of thinking really, and in your research will may be helpful for you. And then the objective function from a very high level perspective, so we can't really build a simpler objective function, but we have to really consider the interactions or the heterogeneities in the more complex reality. And what do we mean by that? It means so with the entity, for example, it's a data or source or value, we have to consider there are couplings, the interactions, there are heterogeneities. And if that from the property perspective, like a distribution or semantic or logic or linkage or dynamic, that could involve non-IIDness there as well. And we talk about interaction. Interaction is a common word widely used in complex system, right? And that could be related to like dependence, correlation, association, matching, semantic, co-occurrence, neighborhood, distance, or density, uncertainty, logic, overlapping, networking, connection, etc., etc. These can all be measured mathematically, right? So there are some of them well measured, some are less well measured, right? So different math techniques, statistical technique to measure these kind of interactions. And as I mentioned, from learning perspective, so if you have multiple methods, multiple models, multiple objectives, multiple tasks, or multiple level of learning, hierarchical learning, for example, and or multiple dimensionality to consider in a learning or process, because multiple process like a coupled hierarchical model, multiple measures to consider in the learning or even the results. Have to consider there, like what I talk about a pattern relation analysis, and there so non-IIDness could be embedded as well. And another important aspect is the context in the environment, right? So whether that's related to other factors, environmental factors, or some constraints, etc., right? So that's what I give you just some high-level structure for you to think where the non-IIDness could exist, and from what perspective you could really think about. And another important thing I want to thing is from the hierarchy perspective, as I showed in some of the examples, from value to attributes to objects to object cluster, and here attribute cluster, feature cluster, or feature set or feature subset, and the data source to multiple method, multiple measure, multiple results, pattern are broadly referred to the learning results after evaluation. So the non-IIDness could appear in some of the stage or over the whole hierarchy. And I think at the inner level, so if we can consider a little bit more, I think there you could see a great opportunity to make a so-called innovation, right? Doesn't matter whether you work on a statistical model, like a deep neural model, or the other mathematical method or evolutionary learning method, I think all this kind of thinking apply. That's my understanding. And there are some fundamental issues for you to think. The first one, how can we determine whether a data set is IID or non-IID? And second, whether association, correlation, causality, dependence, uncertainty, randomness cover all relationships. Three, real-life problems often involve multiple sources, like multiple views, multiple modalities, multiple tasks, multiple domains, etc. Are they identically distributed? What do we mean by heterogeneity? Does identical distribution means homogeneity? And last one, what do we mean by independence in a broader sense? All right. So I listed these questions. I think so you could think in your particular research discipline. If you work in the statistical sense, or if you work in the evolutionary, and I think it could, or numerical or neural, could be integrated in different ways. I mean, in terms of quantification, right? And there are other questions, and there are many. KNN, SVM, decision tree, classic ensemble models, IID. Does classical transfer learning capture non-IIDness? In probabilistic graphical modeling, how non-IIDness is modeled? Do deep neural models capture non-IIDness? If you think yes, to what extent, and where are the gaps, etc., etc. Right. So that's why I see, this is a quite fundamental issue, and also opportunity as well, and it involves almost every specific, machine learning and data analytic area. And so that's basically it. And if you like to know more, you can go to the website. There's some particular page here, it's datascience.org, non-IIDnesses. And I list many references here related to non-IID learning concept, representation learning, discretization, k-means, k-meals, spectral clustering, KNN classification, ensemble clustering, global behavior analysis, image processing, computer vision, statistical relation learning, or outlier detection, feature selection, pattern or rule relation analysis, combined mining, combined pattern mining, and the non-IID recommender system, non-IID document text analysis, keyword query in the QA settings, non-IID similarity matrix learning, and there are many other I didn't really list. So that's about as well as what Jillian illustrate, right? So that's about it. I think now we can have questions. So I think the question what Chen asked Ole. So the first question, I answer your question. So feel free if you guys have any questions, just to give me a text in the chat, or you can unmute yourself. I think the first question what Chen asked is about XE, right? How to determine XE. So I think your question was related to the pattern, the complex pattern. Just go back to there. But you can correct me if I'm wrong. So that's because there I have a XE. So that's more related. Okay, sorry here. That's more related to the pattern. So here, so you have like in the treatment, health treatment, right? So is that right, Chen? Right. So yeah. So if you have like a health treatment, a drug or whatever. So if the first treatment XP and then follow another treatment, and the health condition may change or may not change, we still want to understand, what would be the impact or influence of XE, right? Treatment. It could be one treatment. It could be a sequence of treatment. right? But the mathematically, we want to understand, what is the contribution of XE? So in the frequentist setting, so you can see you got like, if this is a frequent pattern, you can have like, support competence you can lift, right? And if this is a pair, right? With a pair, we can actually calculate the contribution of XE by this way. So you have lift of XP plus XE leader to T, and the lift of XP leader to T, and you got to tell a difference, and then use this way to measure to what extent XE contributed to this T, would be T2 or T1. Right. So that's one way. Another way is we create a PS ratio, and use a PS ratio. You can calculate through a probabilistic way, like this, to measure the contribution of XE to the to this T2. And of course, you can, if there's a T1, T2, you can have a delta T, which is the difference between T2 and T1, and then measure it, right? Okay. So if you want to know a little bit more the whole story about this, there's a paper there to discuss about how to mine important activity or behavior or pattern in the going beyond the traditional frequentist framework in the frequent pattern mining. By the way, so assertion rule mining, we typically do not use it in the industry.